My name is Sarah Chen, and I've been a field geologist for the National Park Service for 8 years now. I've worked in some of the most remote places in this country, from the volcanic fields of Hawaii to the limestone caves of Kentucky. I thought I'd seen every kind of geological oddity nature could throw at me. I was wrong. It was late September of 2022 when I got the assignment to conduct soil stability tests in the backcountry of Glacier National Park. Nothing unusual about it, just routine analysis work for proposed trail expansion near Lake McDonald. The kind of job I'd done dozens of times before. Pack in with my equipment, take samples, run the tests, file the report. Simple. The weather that week was perfect for field work. Clear skies, temperatures in the 60s, no wind to speak of. I'd set up my base camp about 3 miles in from the Apgar Village trailhead, in a small clearing surrounded by lodgepole pines and Douglas firs. The forest was quiet in that way it gets in late fall, when most of the tourists have gone home and the animals are preparing for winter. I spent the first 2 days mapping the area and taking preliminary samples. Everything looked normal, typical glacial till over bedrock, the kind of soil composition you'd expect in that part of Montana. The proposed trail route looked solid, with good drainage and stable substrate. I was actually ahead of schedule, which doesn't happen often in this line of work. It was on the 3rd day that I found it. I was working about 200 yards southeast of my camp, taking core samples with my hand auger. The plan was to drill down about 3 feet, just deep enough to check soil density and composition. I'd already completed 4 sample sites that morning without any issues. The 5th site was in a small depression between 2 large boulders, nothing that stood out as unusual. I started drilling, expecting to hit bedrock within a few feet, like I had at the other locations. But the auger kept going. 3 feet, 4 feet, 5 feet. The resistance felt wrong, not like drilling through soil or even loose sediment. It was more like drilling through air. I pulled the auger out and looked at the bit. It was completely clean. No soil, no rock fragments, nothing. I'd been drilling for 10 minutes and hadn't brought up a single sample. I shined my flashlight down the hole, but the beam just disappeared into darkness. I've been doing this work long enough to know when something doesn't make sense. Soil doesn't just vanish. Rock doesn't form perfect cylindrical voids. There had to be an explanation, maybe an old mine shaft or a natural cave system I wasn't aware of. But there was no record of mining activity in this area, and the geological surveys showed solid bedrock. I decided to use my depth probe, a weighted line that would tell me exactly how deep the void went. I fed the line down slowly, counting off the footage. 10 feet, 20 feet, 30 feet. At 47 feet, the weight finally hit bottom. 47 feet of nothing. A perfect cylinder about 6 inches in diameter, extending straight down through soil and bedrock that should have been solid. I'd never seen anything like it in my entire career. I spent the rest of that day taking measurements and photographs, trying to document everything I could. The walls of the void were smooth, almost polished. When I dropped a small stone down the hole, it took exactly 3.5 seconds to hit bottom. The math confirmed what my depth probe had already told me: 47 feet, give or take a few inches. I called my supervisor, Janet Morrison, on my satellite phone that evening. Janet's been with the Park Service for 25 years, and she's seen more geological oddities than anyone I know. But when I described what I'd found, there was a long pause on the other end of the line. "You're sure about the measurements?" she asked. "Triple-checked everything," I told her. "I've got photos, core samples from the surrounding area, GPS coordinates. Whatever this thing is, it's not natural." Another pause. "Sarah, there's no record of any drilling or excavation in that area. The land's been protected since 1910. Are you absolutely certain there's no material coming up from the hole?" I looked over at my equipment, at the clean auger bit and empty sample containers. "Nothing, Janet. It's like drilling through air." She told me to pack up and come back to headquarters. We'd return the following week with imaging equipment and a proper drilling rig. Whatever this was, we needed to understand it before moving forward with the trail project. I marked the location with flagging tape and GPS coordinates. took one last set of photographs, and hiked out the next morning. The drive back to West Glacier gave me time to think about what I'd found. In all my years of geological study, I'd never encountered anything that defied explanation so completely. Natural processes don't create perfect cylindrical voids. Human activity leaves traces, signatures, in the surrounding soil and rock. This had neither. A week later, I returned with Janet and 2 other team members. We brought ground-penetrating radar, a fiber optic camera system, and enough equipment to properly map and document the anomaly. I was excited to show them what I'd discovered, to finally get some answers about what we were dealing with. But when we reached the coordinates I'd marked, there was nothing there. The flagging tape was gone. The GPS coordinates led us to what looked like undisturbed forest floor, covered with pine needles and small rock. I was certain we were in the right place. The 2 large boulders were exactly as I remembered them, and my GPS was showing the correct location. Maybe we're off by a few yards, Janet suggested. We spent the next 2 hours searching the area, probing the ground with metal rods, looking for any sign of the void I documented. Nothing. It was Tom Bradley, our radar specialist, who found the first indication that something was wrong. His equipment showed a subtle density variation in the soil, right where my GPS coordinates indicated the hole should be. The ground had been disturbed recently, filled in with loose soil and debris. We started digging. 3 feet down, we found it. Or rather, we found where it had been. The void was filled with loose dirt, pine needles, and small rocks. Someone had deliberately packed it full, then scattered organic material on top to make it look natural. It was professional work. If Tom hadn't had the radar, we never would have found it. But who would do this? And why? The area was miles from the nearest road, accessible only by foot trail. Someone had hiked in with tools and materials, spent hours filling a 47-foot deep hole, and carefully concealed all evidence of their work. We excavated about 10 feet down before Janet called a halt. Whatever had been there was gone, and we weren't going to learn anything more by digging. The trail expansion project was quietly canceled, and the area was classified as geologically unstable. That was 6 months ago. I've been back to the site twice since then, always on my own time, always hoping to find some clue I missed. The filled hole is still there, settled now and covered with new growth. It looks like any other patch of forest floor. But sometimes, when I'm lying in my tent during field work in other parts of the park, I think about those smooth walls extending down into darkness, about the 3.5 seconds it took for a stone to hit bottom, about someone hiking miles into the wilderness with the tools and materials needed to erase all evidence of what I'd found. The official report lists the soil analysis as inconclusive due to equipment failure. Janet suggested I not mention the void in my field notes, and I understood why. How do you document something that shouldn't exist? How do you explain a hole that someone went to great lengths to hide? I still have the photographs from that first day, stored on my personal camera. The images show exactly what I remember. A perfect cylindrical void disappearing into darkness, surrounded by undisturbed forest. But sometimes, late at night when I'm reviewing my field notes, I wonder if I really saw what I think I saw. The thing that bothers me most isn't the void itself, or even the fact that someone filled it in. It's the precision of the work. Whoever did this knew exactly where to find a 6-inch diameter hole in thousands of acres of wilderness. They knew how deep it was, how much material they'd need to fill it. That suggests planning, familiarity with the site. It suggests they'd been watching. I've requested assignment to other parks since then. Yellowstone, mostly, where the geology is straightforward and the anomalies have explanations. But I still get calls from other geologists, colleagues who've heard rumors about unusual findings in remote areas, holes that don't belong, voids where there should be solid earth. Each time, I tell them to document everything, take photographs, mark the GPS coordinates, and each time, I wonder if they'll find what I found, evidence of something that defies explanation, followed by evidence that someone very much wants it to stay hidden. I don't know what I discovered in that clearing near Lake McDonald, but I'm certain of one thing. I wasn't the first person to find it. I'm Marcus Rodriguez, and I've been doing mining surveys for the Bureau of Land Management for 14 years. Most of that time's been spent in Arizona and New Mexico, cataloging old claims and abandoned workings for environmental remediation. It's solitary work, but I prefer it that way. Just me, my equipment, and the desert quiet. In early April of 2023, I got assigned to survey the old Esperanza mine complex, about 40 miles northeast of Tucson. The site had been abandoned since 1962, when the copper prices dropped and the company pulled out. Standard procedure: document the shaft conditions, check for environmental hazards, make recommendations for permanent closure. The Esperanza had been a decent-sized operation in its day. 7 main shafts plus a handful of exploratory holes, all carved into a hillside of red sandstone and volcanic rock. The desert had been slowly reclaiming the site for 60 years. Palo Verde and cholla grew up through the old tailings piles, and most of the surface structures had collapsed or blown away. I set up my base camp in the valley below the mine on a Tuesday morning. The weather was perfect for the work: clear skies, temperature in the 70s, no wind. I planned to spend 4 days mapping the shafts and another 2 writing up the report. Routine stuff, the kind of job I could do in my sleep. The first 3 shafts were exactly what I expected. Standard hard rock mining techniques, pick and blast work, nothing unusual about the construction or condition. Some water seepage, typical cave-in damage, old timber supports rotting away. I documented everything with photographs and sketches, measured the dimensions, took air quality readings. It was in the 4th shaft that I found the first one. The shaft angled down about 30 degrees from horizontal, following what had probably been a promising ore vein. I was about 40 feet in when my headlamp caught something unusual in the wall. At first glance, it looked like a natural quartz formation, a cluster of white crystals jutting out from the sandstone. But when I got closer, I could see it had been deliberately shaped. Someone had carved the quartz into a perfect 6-pointed star, about 8 inches across. The work was precise, professional even. Each point was exactly the same length, the angles perfectly symmetrical. But what made me stop and really look were the initials carved in the center: JKH, followed by what looked like 1987. I photographed the carving from multiple angles and added it to my survey notes. It was unusual, sure, but not unheard of. Miners sometimes left marks in the tunnels, signatures or dates to commemorate finds or milestones. The date bothered me. A little 1987 was 25 years after the mine had been officially closed. But it wasn't impossible that someone had been poking around the old workings. The 5th shaft was deeper than the others, extending almost 200 feet into the hillside. I was taking my time with this one, documenting a particularly interesting section where the original miners had followed a quartz vein through multiple rock layers. The geology was complex, beautiful in its own way. About 150 feet in, I found the 2nd star. It was identical to the first one. Same size, same proportions, carved into another natural quartz formation. And the same initials in the center: JKH, 1987. I stood there for several minutes, comparing my photographs from the previous shaft. They matched exactly, down to the smallest details of the carving technique. 2 identical carvings in separate shafts of a mine that had been sealed for decades. I started thinking about access routes, wondering how someone could have gotten into these tunnels in 1987. The mine entrances had been barricaded with concrete barriers and steel grating, but determined people find ways around security measures. The 6th shaft yielded a 3rd star. Same dimensions, same craftsmanship, same initials and date. By now, I was starting to feel uneasy about the whole situation. 3 identical carvings suggested something more than casual trespassing. Someone had spent considerable time and effort working in these tunnels, creating multiple copies of the same design. I found the 4th star in the 7th shaft, the deepest and most remote of the mine workings. This one was different in one crucial way. The quartz formation around it showed fresh tool marks, as if someone had been working on it recently. The rock dust hadn't had time to weather and discolor like the others. That evening at my camp, I called my supervisor, Elena Vasquez, and described what I'd found. Elena's been with BLM for 28 years and has seen everything the desert can throw at you. But even she seemed puzzled by the identical carvings. "You're sure about the dates?" she asked. "All of them say 1987? Every one. Same initials, too. J, K, H." There was a pause. "Marcus, I want you to do me a favor. Check with the local sheriff's office. See if they have any records for those initials. Missing persons reports. Anything from that time period." I drove into town the next morning and spent 2 hours at the Pinal County Sheriff's Department, going through old files with Deputy Sharon Wells. It didn't take long to find what we were looking for. Jennifer K. Hoffman, 23 years old, disappeared while hiking alone in the Superstition Wilderness in October of 1987. Her car had been found at the Peralta Trailhead, about 20 miles southwest of the Esperanza mine. Search and rescue had spent 2 weeks looking for her, but never found any trace. Deputy Wells pulled out the original case file and showed me Jennifer's driver's license photo. She'd been a graduate student at Arizona State, studying geology. The family had offered a reward, hired private investigators, even brought in psychics. Nothing had ever turned up. Case is still technically open, Wells told me. But after 36 years, we're not expecting any new leads. I drove back to the mine that afternoon with a growing sense of unease. The identical carvings took on a different meaning now. Jennifer Hoffman had been a geology student who disappeared not far from the mine site. Had she been exploring the old workings when something happened to her? Had she carved those stars as some kind of marker or signal? But that still didn't explain the fresh tool marks I'd seen on the fourth carving, or how someone could have accessed sealed mine shafts in the first place. I spent my final day at the site, going through the tunnels one more time, looking for anything I might have missed. In the 7th shaft, I found something that made my blood run cold. Behind the 4th star, carved into the tunnel wall in letters so faint I'd missed them the first time, were the words, "Still Here." The lettering style matched the initials on the stars, but the carving was definitely recent. The rock dust was still fresh, and I could see individual chisel marks in the stone. Someone had been in this tunnel within the past few weeks, maybe even days. I packed up my equipment and drove straight to the sheriff's department. Deputy Wells listened to my story without interrupting, taking notes on everything I'd found. She promised to send a team out to investigate the mine site, but warned me that it might take a few days to arrange. 2 weeks later, I got a call from Elena. The sheriff's department had searched the mine complex and found nothing unusual. No recent signs of entry, no additional carvings, no evidence that anyone had been in the tunnels recently. The concrete barriers were intact, the steel grating undisturbed. They had found the 4 quartz stars I documented, but according to their report, the carvings appeared to be decades old, weathered and discolored by time. There was no mention of the fresh tool marks I'd photographed, or the "Still Here" message I'd found in the 7th shaft. I've been back to the Esperanza site 3 times since then, always on my own time. The mine entrances are sealed exactly as I left them, but something feels different about the place. The desert quiet seems heavier somehow, more watchful. I've never found any new evidence of recent activity, but I can't shake the feeling that someone is still there, still working in those dark tunnels. The official report classified the site as low priority for environmental remediation. No immediate hazards, no evidence of recent disturbance, no threats to public safety. The Esperanza mine remains abandoned and forgotten, slowly disappearing back into the desert. But sometimes, when I'm working other sites in the area, I think about those identical stars carved into solid rock, about a missing geology student who vanished 36 years ago, 20 miles from where her initials appeared in a sealed mine shaft, about fresh chisel marks in stone, and words that shouldn't have existed. The thing that bothers me most is the precision of those carvings. Each star was exactly the same, carved with the kind of skill that comes from practice and repetition. Jennifer Hoffman had been studying geology, But her academic records showed no training in stone carving or mining techniques. So who carved those stars? And if Jennifer disappeared in 1987, who's been maintaining them all these years? I still carry the photographs in my field notes, proof of what I found in those dark tunnels. Sometimes I take them out and study the details, looking for clues I might have missed. The stars are beautiful in their own way, perfect geometric forms carved into ancient stone. But I can't look at them without thinking about those two words hidden behind the fourth star, carved fresh into the tunnel wall where no one should have been able to reach them. Still, here, someone is still there, still working in the darkness beneath the desert. And I have the terrible feeling that someday I'm going to find out who. My name is Rebecca Foster, and I've been an environmental geologist with the Minnesota Pollution Control Agency for 11 years. I've worked contamination sites across the state, from old mining operations in the Iron Range to industrial spills along the Mississippi. I know how to read rock layers, how to date sediments, how to trace pollutants through soil and groundwater. Geology follows rules, predictable, measurable rules that have held true for millions of years. Until last September, I'd never seen those rules broken. I was assigned to investigate potential groundwater contamination near Silver Bay, about an hour northeast of Duluth. A small manufacturing plant had been operating there since the 1950s, and recent testing had detected elevated levels of industrial solvents in nearby wells. Standard environmental assessment work mapped the geology, traced the contamination plume, determined the extent of the problem. The site was on a bluff overlooking Lake Superior, surrounded by the kind of mixed forest you see all along the North Shore. Birch and aspen mixed with pine and fir, the leaves just starting to turn yellow and orange. The lake stretched out to the horizon, gray-blue under an overcast sky. I'd worked dozens of sites with similar geography, and I expected to find the usual geological profile: glacial till over Precambrian bedrock, maybe some lake sediments from when Superior was smaller. I set up my equipment on a Tuesday morning in early September. The weather was cool but pleasant, temperature in the low 60s with a light breeze off the lake. I planned to spend 3 days taking core samples and mapping the subsurface geology, then another 2 days analyzing the contamination pattern. The first day went exactly as expected. I drilled 6 sample holes in a grid pattern around the plant, each one going down about 20 feet through soil and sediment to bedrock. The geology was textbook: 3 feet of topsoil and organic matter, then glacial till deposited during the last ice age, then lake sediments laid down over thousands of years, and finally the ancient bedrock that forms the backbone of the Canadian Shield. I photographed each core sample, labeled the different layers, and took detailed notes on the composition and age of each stratum. Everything fit the standard geological timeline for the area. Recent organic material at the top, glacial deposits from about 12,000 years ago in the middle, older lake sediments below that, and at the bottom, Precambrian limestone formed over 50 million years ago. By evening, I had a clear picture of the site geology and a good understanding of how contaminants might move through the different soil layers. I packed up my equipment, secured the sample holes with temporary caps, and drove back to my hotel in Duluth, feeling satisfied with the day's work. I returned early the next morning to continue sampling. The weather had turned colder overnight, with a thick fog rolling in off the lake. Visibility was down to maybe 50 feet, and everything felt muted and gray. I decided to re-examine the core samples from the previous day before moving on to new locations. That's when I noticed the first discrepancy. Sample hole number 3 showed a geological profile that didn't match my notes from the day before. According to my field book, the limestone bedrock should have been at 18 feet down. But when I measured the exposed core, the limestone was at 6 feet, well above where it should have been. I assumed I'd made an error in my measurements and rechecked everything. The limestone was definitely at 6 feet. More troubling was what lay below it. Instead of finding older rock beneath the limestone, I found glacial till loose sediment full of rounded stones and clay that should have been much higher up in the profile. The chronological order had been reversed. Recent glacial deposits were below 50-million-year-old bedrock. I spent the morning re-examining all 6 sample holes. Every single one showed the same impossible profile. The limestone had moved up several feet overnight, and the younger sediments had somehow ended up below rock that was millions of years older. Geology doesn't work that way. Sediments are deposited in chronological order, with older layers at the bottom and younger layers at the top. It's one of the fundamental principles of the science, established over 2 centuries ago. Rock layers don't reverse their positions overnight. I photographed everything again, taking detailed shots of each core sample and measuring the exact depth of each geological boundary. Then I compared the new photos to the ones I'd taken the previous day. The differences were undeniable. The rock layers had physically rearranged themselves in a pattern that violated every principle of geological science. I called my supervisor, Dave Carlson, on my cell phone and tried to explain what I was seeing. Dave's been a geologist for 30 years, and he's encountered every kind of site condition you can imagine. But when I described the reversed stratigraphy, there was a long silence on the other end of the line. "Rebecca, are you sure you didn't mix up the sample labels?" he asked. "Sometimes when you're working multiple holes, it's easy to get confused about which core came from where." I looked at my photographs, at the careful documentation I'd done the previous day. "No mix-up, Dave. I've got GPS coordinates for each hole, sequential photos, detailed field notes. The stratigraphy has actually changed." Another pause. "That's not possible. Rock layers don't rearrange themselves overnight." "I know, but I'm looking at it right now." Dave told me to pack up and return to the office. We'd review the data together and figure out what had gone wrong. But I couldn't shake the feeling that nothing had gone wrong with my work. Something had gone wrong with the geology itself. I drove back to Duluth that afternoon with a growing sense of unease. I'd been doing this work for over a decade, and I'd never seen anything that defied explanation so completely. Environmental sites could be complex, contamination patterns could be surprising, but the underlying geology was always predictable. Always. The next morning, Dave and I returned to the site together. He brought additional equipment, ground-penetrating radar, a more sophisticated drilling rig, instruments that could provide precise measurements of soil density and composition. We were going to solve this mystery with better data and more careful analysis. But when we reached the sample locations, we found something even more disturbing than reversed stratigraphy. The rock layers had changed again. The limestone that had been at 6 feet the previous day was now at 12 feet. The glacial till that had been below the limestone was back above it, but in a different arrangement than I'd originally documented. It was as if the entire geological profile was slowly shifting, rearranging itself according to rules I didn't understand. Dave spent the morning taking new core samples and running ground-penetrating radar surveys. His instruments confirmed what I'd been seeing. The stratigraphy was genuinely different from one day to the next. Rock layers that should have been stable for millions of years were moving around like loose sand in a bucket. "I've never seen anything like this," Dave admitted as we packed up the equipment. "The geology here should be stable. We're on the Canadian Shield, some of the oldest, most stable rock on Earth." That afternoon, we met with Dr. Sarah Chen, a research geologist from the University of Minnesota. Sarah specializes in Great Lakes geology, and if anyone could explain what we were seeing, it would be her. But when we showed her our photographs and data, she was as puzzled as we were. "This violates basic principles of stratigraphy," she said, studying the images. "Rock layers are deposited in sequence and remain in that sequence unless disturbed by major geological events, earthquakes, glacial action, volcanic activity. There's no evidence of any such disturbance in this area." She paused, looking at the photos again. "Are you absolutely certain these samples came from the same location on different days?" We showed her the GPS coordinates, the sequential photographs, the detailed field notes. Everything confirmed that we'd been sampling the same spots repeatedly, but finding different geological profiles each time. Dr. Chen agreed to visit the site and conduct her own investigation. 2 days later, the three of us returned to the bluff, overlooking Lake Superior. The fog had lifted, and the lake sparkled blue-green under clear skies. It was a beautiful day for fieldwork, but when we reached the sample locations, we found that the geology had changed again. This time, the limestone was at 15 feet down, deeper than it had been in any of our previous measurements. Above it, we found lake sediments, glacial till, and organic topsoil in their proper chronological order. The stratigraphy looked normal, textbook perfect. Dr. Chen took her own core samples and ran additional tests. Everything checked out. The geology was exactly what you'd expect to find at a site like this: stable, predictable, following all the established rules of sediment deposition and rock formation. "I'm not sure what you saw before," she told us as we reviewed her data, "but the geology here is completely normal. Textbook stratigraphy, nothing unusual about it." We showed her our photographs from the previous visits, but she pointed out that camera angles and lighting could be deceiving, that it was easy to misinterpret complex geological relationships without proper analysis. She suggested that we'd probably made some measurement errors or sample mix-ups during our initial investigation. The official report classified the site geology as stable and predictable. The contamination assessment proceeded normally, and we identified the source of the groundwater pollution within a few weeks. The manufacturing plant agreed to install remediation systems, and the case was closed. But I still have the photographs from those first 2 days, stored on my personal camera and backed up on my computer. The images clearly show limestone bedrock at 6 feet, then 12 feet, then 15 feet in the same sample hole on consecutive days. They show glacial sediments below 50-million-year-old limestone, an arrangement that shouldn't exist anywhere on Earth. I've been back to the site twice since then, always on my own time. The geology appears stable now, exactly what Dr. Chen documented during her investigation. But sometimes, when I'm standing on that bluff overlooking Lake Superior, I wonder if the rock layers are still moving, still shifting, according to rules I don't understand. The thing that bothers me most isn't the impossibility of what I saw. It's the precision of the changes. The limestone didn't just move randomly, it shifted to specific depths. 6 feet, then 12 feet, then 15 feet, like it was following a pattern, responding to some kind of schedule or signal. I've requested assignment to other regions since then. I work mostly in the Twin Cities now, where the geology is well mapped and predictable. But I still get calls from other environmental geologists, colleagues who've encountered unusual stratigraphy in remote areas, rock layers that don't match the historical surveys, sediments that seem to be in the wrong order. Each time, I tell them to document everything, take detailed photographs, get second opinions from research universities, and each time I wonder if they're seeing what I saw, evidence that the fundamental rules of geology aren't as permanent as we thought. I don't know what caused the rock layers to shift beneath that bluff, overlooking Lake Superior, but I'm certain of one thing. For 3 days in September, the geology at that site defied every principle of the science I've devoted my career to understanding. And sometimes, late at night when I'm reviewing my field notes, I wonder if it's still happening. If somewhere out there, 50-million-year-old limestone is slowly rising through layers of recent sediment, following rules that exist outside our understanding of how the Earth works. I'm James Park, and I've been a seismic researcher with the United States Geological Survey for 16 years. Most of that time has been spent monitoring volcanic and geothermal activity in Yellowstone National Park. I know every hot spring, every geyser, every thermal feature in the park better than I know my own neighborhood. The ground temperature patterns are as familiar to me as the rhythm of my own heartbeat, which is why what I found in October of 2023 still keeps me awake at night. I was conducting a routine geothermal survey in the backcountry north of the Grand Loop Road, about 8 miles from any established trail. This was part of our ongoing effort to map underground thermal activity and monitor changes in the Yellowstone caldera system. Standard procedure: hike in with portable instruments, take temperature readings at predetermined grid points, log the data, and hike out. The area I was surveying was typical Yellowstone backcountry. Mixed conifer forest, mostly lodgepole pine with some Douglas fir and Engelmann spruce. The ground was covered with a thick layer of pine needles and fallen leaves, and the air had that crisp bite you get in the mountains when winter's coming. No thermal features were visible in the area. No steam vents or hot springs. Nothing to suggest unusual geothermal activity. I'd been working the grid for about 3 hours when I reached point 17, a location that should have been completely unremarkable. My handheld thermal probe showed normal ground temperature about 45 degrees Fahrenheit, exactly what you'd expect for October soil in that elevation and climate. But when I moved 10 feet to the east for point 18, my instruments went crazy. The temperature reading spiked to 247 degrees Fahrenheit. I thought the probe had malfunctioned, so I checked the calibration and tested it on some nearby soil. It read normal temperatures everywhere else, but when I moved back to that specific spot, it showed the same impossible reading. 247 degrees would be hot enough to boil water, hot enough to burn through boot leather in seconds. But I wasn't feeling any heat. The ground looked normal. No steam, no discoloration, no signs of thermal activity. I could walk on it without any discomfort. I spent the next hour mapping the thermal anomaly with my instruments. The hotspot formed a perfect circle 30 feet in diameter, not roughly circular, not approximately round, geometrically perfect, as if someone had drawn it with a compass. The temperature was uniform across the entire circle, exactly 247 degrees at every measurement point. Outside the circle, ground temperatures were completely normal. I've worked geothermal sites for 16 years, and I've never seen anything like it. Thermal features in Yellowstone are created by underground hot water and steam systems, and they follow predictable patterns. They're irregular in shape, varying in temperature, and always accompanied by visible signs: steam, mineral deposits, altered soil chemistry. This was none of those things. I documented everything with photographs and GPS coordinates, took detailed notes on the size and temperature of the anomaly, and collected soil samples from inside and outside the thermal circle. Then, I hiked back to my vehicle and drove straight to the Yellowstone Volcano Observatory office in Mammoth Hot Springs. My supervisor, Dr. Lisa Martinez, has been monitoring Yellowstone's geothermal systems for 22 years. She's seen every kind of thermal anomaly the park can produce, from new hot springs forming overnight to geysers changing their eruption patterns. But when I showed her the data from point 18, she frowned and asked me to double-check my instruments. 247 degrees with no visible thermal activity? She said. That's not possible. At that temperature, you'd see steam, mineral precipitation, changes in vegetation, something. I showed her the photographs I'd taken at the site. The ground inside the thermal circle looked identical to the ground outside it. No steam, no dead vegetation, no signs of heat whatsoever. Just normal forest floor, covered with pine needles and fallen leaves. James, I need you to go back tomorrow with the full survey team, Dr. Martinez said. We need to understand what's causing this before we can file a report. The next morning, I returned to the site with 3 other researchers and a full load of monitoring equipment. We brought ground-penetrating radar, seismometers, gas detection instruments, and thermal imaging cameras. If there was an underground heat source causing the anomaly, we were going to find it. But when we reached the coordinates I'd marked the day before, my handheld thermal probe showed normal ground temperature, 45 degrees Fahrenheit, exactly what you'd expect for October soil at that elevation. I checked and rechecked the GPS coordinates. We were in the right location. I could see the small orange flags I'd used to mark the thermal circle, but there was no temperature anomaly, no sign that anything unusual had ever occurred at the site. Maybe it was a temporary event, suggested Dr. Fall. Karen Williams, our geochemist. Underground hot water systems can be unpredictable. A thermal pulse could have reached the surface temporarily and then dissipated. But thermal pulses don't form perfect circles, and they don't disappear without leaving any trace in the soil chemistry or groundwater system. We spent 4 hours conducting a thorough survey of the area. The ground-penetrating radar showed normal soil layers with no underground cavities or heat sources. The seismometers detected no unusual vibrations or underground activity. Gas detection instruments found normal atmospheric composition, with no volcanic gases or hydrogen sulfide. It was Dr. Williams who found the boots. She was collecting soil samples from the center of where the thermal circle had been when she called out to the rest of us. "James, you need to see this." Arranged in a perfectly straight line at the exact center of the thermal anomaly were 7 pairs of hiking boots, not scattered randomly, not left in a pile arranged with military precision, each pair exactly 3 feet from the next, all facing the same direction toward magnetic north. The boots were in various conditions. Some looked relatively new, others were weathered and faded as if they'd been exposed to the elements for years. Different brands, different sizes, different styles, but all hiking boots, all arranged with the same careful precision. "How long do you think these have been here?" asked Tom Bradley, our seismologist. I studied the boots more carefully. Some showed rust on the metal eyelets and buckles, suggesting they'd been exposed to weather for extended periods. Others looked like they might have been placed recently. The arrangement was too precise to be accidental, too deliberate to be natural. "They weren't here yesterday," I said. "I walked through this exact area multiple times taking measurements. I would have noticed them." We photographed the boots from multiple angles and recorded their GPS coordinates. Dr. Williams collected additional soil samples from around each pair, looking for any trace evidence that might explain how they'd gotten there. But the most disturbing thing wasn't the boots themselves, it was their condition. None of them showed signs of being removed forcibly. No torn laces, no damaged leather, no indication that they'd been pulled off someone's feet against their will. They looked like they'd been removed normally and placed carefully in position. 7 pairs of boots. 7 missing people, possibly. We spent the rest of the afternoon searching the immediate area for any other evidence, clothing, camping gear, signs of human activity. We found nothing. Just 7 pairs of hiking boots arranged in a line where a 247-degree thermal anomaly had existed the day before. Dr. Martinez contacted the park's law enforcement division that evening. Chief Ranger Patricia Collins and 2 of her officers hiked out to the site the next day to conduct their own investigation. They photographed the boots, recorded their positions, and ran the serial numbers through missing persons databases. 3 of the boots matched reports of missing hikers dating back over the past 5 years. Different times of year, different areas of the park, no apparent connection between the cases. The other 4 pairs couldn't be traced to any specific incidents. We've had people go missing in Yellowstone for as long as there's been a park. Chief Collins told me when I asked about the cases. Usually they wander off trail and get lost, or they have accidents in remote areas. We find most of them eventually, but not all. The boots were collected as potential evidence, but the cases remained open with no new leads. The official report classified the thermal anomaly as equipment malfunction and the boots as unrelated to park operations. No connection was established between the temperature readings and the arranged footwear. But I know what I measured at that site. 247 degrees in a perfect 30-foot circle, with no visible signs of thermal activity and no underground heat source. Temperature readings that disappeared overnight, leaving behind 7 pairs of boots arranged with mathematical precision. I've been back to the coordinates 3 times since then, always on my own time. The ground temperature remains normal, and there's no sign that the boots were ever there. But sometimes, when I'm taking readings in other parts of the park, I think about those 7 pairs of hiking boots lined up like soldiers at attention. The thing that bothers me most is the precision of the arrangement. Boots don't arrange themselves in straight lines. People don't remove their footwear and place it in geometric patterns before disappearing. Someone, or something, had taken great care to position those boots exactly 3 feet apart, all facing the same direction. But who? And why? I still carry the photographs from that day in my field notes, proof of what we found at the thermal anomaly site. Sometimes I take them out and study the details, looking for clues I might have missed. The boots are various sizes, men's and women's, different age ranges based on the styles and wear patterns. 7 people who hiked into Yellowstone's backcountry and never hiked out. 7 pairs of boots left behind in a place where the laws of physics had briefly stopped working. I don't know what caused the temperature anomaly, or why those boots were arranged the way they were, but I'm certain of one thing. Somewhere in Yellowstone's 2 million acres of wilderness, there are 7 people walking around without their shoes. And I have the terrible feeling that they're not walking by choice. My name is Linda Hartwell, and I've been a hydrogeologist with the Washington State Department of Ecology for 13 years. I specialize in groundwater assessment and aquifer mapping, mostly in the Pacific Northwest, where the geology can be complex and unpredictable. I've drilled test wells through every kind of rock and soil formation you can imagine, from coastal sediments to volcanic ash layers to ancient metamorphic bedrock. I thought I understood how water moves through the ground, how rock formations behave under pressure, how drilling equipment responds to different geological conditions. I was wrong about all of it. In November of 2022, I was assigned to investigate potential groundwater contamination in Olympic National Forest, about 20 miles west of Port Angeles. A small logging operation had been using diesel fuel storage tanks in the area during the 1980s, and recent soil testing had detected petroleum hydrocarbons in a nearby creek. Standard environmental work drill monitoring wells mapped the groundwater flow, determined if contamination had reached the local aquifer. The site was typical Olympic Peninsula forest. Dense stands of Douglas fir and western hemlock, thick understory of salal and Oregon grape, everything draped with moss and ferns. The air was heavy with moisture, even though it hadn't rained for 2 days. It's the kind of place where sound gets muffled by the vegetation, where you can feel completely isolated even though you're only a few miles from a paved road. I set up my drilling rig on a Tuesday morning in early November. The equipment was a truck-mounted rotary drill, standard for this kind of work, powerful enough to bore through rock, precise enough to install monitoring wells in exactly the right locations. I plan to drill 4 test holes to a depth of about 50 feet, reaching the regional water table and mapping the groundwater flow direction. The first 3 holes went exactly as expected. I drilled through about 10 feet of forest soil and organic matter, then hit a layer of glacial till deposited during the last ice age. Below that was fractured basalt bedrock, part of the Columbia River basalt group that underlies much of western Washington. The rock was hard, but not unusually so, and my drill bit made steady progress through the basalt layers. I reached the water table at 38 feet in each hole, exactly where the geological surveys predicted it would be. I installed plastic monitoring well casings, sealed them properly, and marked each location with GPS coordinates. Routine work, the kind of job I'd done hundreds of times before. The 4th hole was different from the start. I was drilling in a small clearing about 100 yards from the other 3 wells, following my predetermined grid pattern. The surface geology looked identical, same soil layers, same glacial deposits, same basalt bedrock. But my drill bit was meeting less resistance than it should have. At 15 feet down, the resistance disappeared completely. The drill bit suddenly dropped about 3 feet, like it had broken through into an open space. The drill motor revved up as the bit spun freely in what should have been solid rock. I pulled back on the controls and tried to understand what was happening. I've drilled through cave systems before, and I know what it feels like when you hit a natural void in the rock. This was different. The drill had been progressing normally through solid basalt, then suddenly broke through into empty space. Natural caves don't form in basalt like that. You need limestone or other soluble rock. for significant underground cavities to develop. I lowered the drill string slowly, trying to feel what was below. The bit dropped another 5 feet before I felt resistance again, but it was the wrong kind of resistance. Instead of hitting the bottom of a small cavity, the drill bit felt like it was hanging up on loose material, rocks, soil, debris. That's when I heard the sound. It was faint, barely audible over the noise of the drill motor, but it sounded like metal clanging against metal somewhere deep underground. I shut off the drill and listened. For a moment, there was only the normal forest quiet wind in the trees, distant bird calls, water dripping from moss-covered branches. Then I heard it again. Metal striking rock, echoing from somewhere far below where my drill bit should have been. I tried to raise the drill string, but it wouldn't budge. Something was holding it down there. Either debris blocking the hole, or the bit itself jammed against the walls of whatever cavity I'd broken into. I applied more lifting force, gradually increasing the pressure until I was pulling with everything the rig could generate. The drill string came up fast when it finally broke free, faster than it should have. When I examined the bit, I found that the entire drilling assembly bit, drill collar, and about 20 feet of steel pipe was missing. The drill string had sheared off cleanly, as if it had been cut with industrial equipment. I've been drilling test wells for 13 years, and I've never lost equipment like that. Drill bits wear out, pipes get stuck occasionally, but you don't lose 20 feet of heavy steel drilling equipment to a 15-foot hole in basalt bedrock. I marked the whole location and drove back to the office to report what had happened. My supervisor, Gary Chen, listened to my description without interrupting, but I could see the skepticism in his expression. Drilling equipment doesn't just disappear into solid rock. Linda, are you sure about the depth? He asked. 15 feet isn't deep enough to hit significant groundwater or underground cavities. I showed him my drilling logs, the careful notes I'd taken on each foot of progress through the different rock layers. The geological profile was normal until the drill bit hit whatever void existed at 15 feet down. Gary agreed to return to the site with me the next day. We brought additional equipment, a backup drilling rig, groundwater probes, and a fiber optic inspection camera that could be lowered into the hole to see what was down there. When we reached the site, I found that the hole had been covered with a heavy steel plate and marked with orange warning flags. I hadn't put those there. Gary looked as puzzled as I felt. Maybe someone from the Forest Service secured the hole, he suggested. They don't like open excavations in public areas. But when we called the local ranger station, they had no record of anyone visiting the site. The steel plate and warning flags had appeared overnight, placed by someone who knew about the drilling accident and wanted to mark the hazard. We removed the steel plate and lowered the inspection camera into the hole. The fiber optic cable had lights and a video recorder, designed to provide visual documentation of well conditions and underground geology. I'd used similar equipment dozens of times to inspect monitoring wells and underground storage tank sites. The camera descended normally for the first 15 feet, showing the same rock layers I'd drilled through the day before. Then it reached the void where my drilling equipment had disappeared. The cavity was much larger than I'd expected. The camera lights illuminated a rough-walled chamber extending beyond the range of visibility, carved into what should have been solid basalt bedrock. I could see pieces of my missing drilling equipment scattered across the floor of the chamber, twisted steel pipe, broken drill bits, metal debris that shouldn't have existed. But the most disturbing thing wasn't what I could see. It was what I could hear. The camera's audio pickup was recording sound from the chamber, and as we lowered it deeper into the void, we started hearing voices, faint at first, like distant conversation, but becoming clearer as the camera descended. Someone was calling for help from somewhere much deeper in the chamber system. A woman's voice echoing off the rock walls, pleading for someone to find her. The voice was distorted by the acoustics of the underground space, but it sounded familiar. Gary and I looked at each other in confusion. There was no way anyone could be down there. The chamber was 15 feet below ground, accessible only through the narrow hole my drill bit had created, and the voice sounded like it was coming from much deeper than our camera had reached. I called out toward the hole, trying to communicate with whoever was down there. "Hello? Can you hear me? We're going to get help." The response made my blood turn cold. The voice that came back from the chamber was my own voice, calling the exact words I'd just spoken. But the echo was wrong. It was coming from deeper in the system than sound should have been able to travel, and it arrived several seconds after I'd spoken. Gary stared at the camera monitor, then at me, then back at the monitor. "Linda, that's not possible. Sound doesn't work that way underground." I tried again, calling different words into the hole. "Can you tell us your name?" My own voice echoed back from the chamber depths. "Can you tell us your name?" But the timing was wrong. The acoustics were wrong. And the voice seemed to be coming from a distance that couldn't exist 15 feet below ground. We spent the next hour lowering the camera deeper into the chamber system, following what appeared to be a network of connected cavities extending far into the earth. The geological formations we saw on the video didn't match anything in the regional surveys. These weren't natural caves carved by water action. They looked deliberately excavated, with tool marks visible in the rock walls. And throughout the exploration, we kept hearing voices, multiple people calling for help, conversations in languages I didn't recognize, sounds that seemed to come from everywhere and nowhere at once. Every time I spoke into the hole, my own voice would echo back from impossible depths, sometimes repeating words I hadn't said yet. The camera cable ran out at 200 feet. We descended that far into a chamber system that shouldn't have existed, in an area where geological surveys showed solid bedrock extending to depths of over 1,000 feet. Gary contacted the U.S. Geological Survey and the National Speleological Society, trying to find experts who could explain what we'd discovered. But when their teams arrived 2 days later, they found only a normal test hole, extending 15 feet into basalt bedrock. The chamber system was gone. The cavity that had swallowed my drilling equipment had somehow filled itself with solid rock. The fiber optic camera, which we'd left in the hole overnight, was found coiled neatly on the surface, with no sign that it had ever been underground. The official report classified the incident as equipment failure during routine drilling operations. The missing drilling equipment was written off as a loss, and the environmental assessment continued using different methods. But I still have the video footage from that day, stored on my personal laptop and backed up to multiple drives. The images clearly show a vast underground chamber system carved into rock that should have been solid, filled with voices that shouldn't have existed. I've been back to the site 4 times since then, always on my own time. The test hole is still there, exactly 15 feet deep, ending in solid basalt bedrock. But sometimes, when I lean over the hole and listen carefully, I can still hear faint voices calling from somewhere far below. The thing that haunts me most isn't the impossible geology or the missing equipment. It's the sound of my own voice calling for help from depths that can't exist, repeating words I hadn't spoken yet, echoing from a place that geological science says isn't there. Someone is still down there, calling from a chamber system that exists outside our understanding of how rock and space and sound work underground. And I have the terrible feeling that someday I'm going to answer back. I'm Tom Brennan, and I've been a water quality specialist with the New York State Department of Environmental Conservation for 19 years. Most of that time has been spent monitoring streams and lakes in the Adirondack Park, testing for pollutants, tracking seasonal changes in water chemistry, and investigating reports of contamination. I know these waterways like other people know their neighborhood streets, every bend, every tributary, every quirk of flow and seasonal behavior, which is why what happened at Beaver Creek in September of 2023 still doesn't make sense to me. I was conducting routine water quality monitoring as part of our ongoing assessment of acid rain impacts in the central Adirondacks. Beaver Creek is a small tributary of the Raquette River, flowing northeast through about 12 miles of mixed hardwood and conifer forest. It's a typical Adirondack stream clear water running over granite bedrock, moderate flow rates, stable chemistry year-round. I'd been monitoring this particular section of Beaver Creek for 8 years, taking monthly samples from the same 5 collection points along a 3-mile stretch. The data was consistent and predictable. Slightly acidic water, typical of streams draining granitic terrain, low mineral content, no significant pollution sources in the watershed. The weather that September was typical for the season. We'd had a dry summer, but no drought conditions. A few scattered thunderstorms in late August had brought the water levels back to normal, and early fall temperatures were keeping evaporation rates low. Nothing unusual about the hydrological conditions in the region. I started my sampling run at the upstream collection point, a small pool where the creek flows under a logging road bridge. Standard procedure: measure water temperature, dissolved oxygen, pH, and conductivity. Then collect samples for laboratory analysis of nutrients and trace metals. The first thing I noticed was that the water level seemed higher than it should have been, given the recent rainfall patterns. Not dramatically higher, but enough to be noticeable. The creek was running fuller than I'd seen it in months, despite the fact that we hadn't had significant precipitation in over 2 weeks. The second thing I noticed was the sound. I've been listening to the sound of moving water for nearly 2 decades, and you develop an ear for the normal patterns. Fast water over rocks sounds different from slow water through pools. Shallow riffles have a different acoustic signature than deep runs. The sound of Beaver Creek that morning was wrong, subtly wrong, but definitely wrong. It took me about 10 minutes to figure out what was bothering me. The creek was flowing backward, not dramatically backward, not like a flash flood or dam failure that reverses flow temporarily. The water was moving in the opposite direction from normal, but at the same steady pace it always maintained. Upstream had become downstream. The creek that had flowed northeast toward the Raquette River for thousands of years was now flowing southwest toward its headwaters. I checked my GPS coordinates to make sure I was at the right location. I was. I checked the streamflow direction against my compass. The water was definitely moving southwest, uphill according to the topographic maps, against the natural gradient of the terrain. Water doesn't flow uphill. It's one of the most basic principles of hydrology, as fundamental as gravity itself. Streams follow the path of least resistance downslope, from higher elevations to lower elevations, always moving toward the ocean eventually. Beaver Creek had been flowing in the same direction since the glaciers retreated 12,000 years ago. I spent the next hour walking the entire 3-mile section I normally monitored, checking the flow direction at each sampling point. The creek was flowing backward along its entire length, moving steadily against the natural gradient with no apparent source of energy to drive the reversed flow. I collected water samples at each location and ran field tests for basic chemistry parameters. Everything looked normal: temperature, pH, dissolved oxygen levels, all within the expected ranges for September conditions. The water was clear, with no unusual odors or visible contamination. But when I ran the conductivity tests, I found something that made no sense. Electrical conductivity in stream water is determined by dissolved minerals, salts, metals, and other ions that conduct electricity. Each watershed has a characteristic mineral signature based on the geology of the region. Adirondack streams like Beaver Creek typically show low conductivity because the granite and gneiss bedrock doesn't contribute many dissolved minerals to the water. The conductivity readings I was getting were 3 times higher than normal for Beaver Creek. The water contained elevated levels of calcium, magnesium, and sulfate ions that shouldn't have been present in this watershed. I ran the tests multiple times, using different instruments and fresh calibration solutions. The results were consistent. Beaver Creek was carrying dissolved minerals that had no geological source in the Adirondack region. When I got back to the office that afternoon, I immediately sent the water samples to our laboratory for comprehensive chemical analysis. Then I spent several hours reviewing historical data for Beaver Creek, looking for any precedent for the flow reversal and unusual chemistry. The laboratory results came back 3 days later, and they were even more disturbing than the field measurements had suggested. The water contained trace minerals that were geologically impossible for the Adirondack region. Strontium isotopes that indicated limestone bedrock. Rare earth elements associated with clay-rich sedimentary formations. Chemical signatures that matched watersheds hundreds of miles to the south. I compared the mineral profile to our statewide database of stream chemistry data, looking for a match. I found one, but it didn't make sense. The chemical signature was identical to Cannonsville Creek in the Catskill Mountains, about 200 miles southwest of Beaver Creek. But Cannonsville Creek had been dry for 3 years, drained by a prolonged drought that had left the streambed completely dewatered. I called Dr. Jennifer Walsh, a hydrologist at the State University of New York, who had been studying Catskill Mountain hydrology for 25 years. Jennifer was familiar with both watersheds and had published papers on regional differences in stream chemistry. "Tom, that's impossible," she said when I described the mineral analysis results. "Cannonsville Creek hasn't had flowing water since 2020. Even if it did, there's no hydrological connection between the Catskills and the Adirondacks. Different river systems, different geology, different everything." I sent her copies of the laboratory reports and field data. She called me back the next day, sounding puzzled and concerned. "I've reviewed your data, and I can't explain it," she admitted. "The mineral signatures are definitely consistent with Catskill geology, but I have no idea how that water could have gotten to Beaver Creek." I returned to Beaver Creek the following week with additional monitoring equipment. I wanted to document the flow reversal with more sophisticated instruments and collect additional water samples for isotope analysis. But when I reached the first sampling point, I found that the creek was flowing in its normal direction again, northeast toward the Raquette River, following the natural gradient of the terrain. The water level was back to normal for the season, and the sound of the flowing water matched what I'd been hearing for 8 years. I collected new water samples and ran field tests for basic chemistry. Everything was normal. Conductivity levels typical for Adirondack streams. Mineral content consistent with granite bedrock. No trace of the unusual ions I detected the week before. The laboratory analysis confirmed what the field tests had shown. The water chemistry was exactly what you'd expect for Beaver Creek: low mineral content, slightly acidic pH, chemical signature consistent with local geology. I filed a report documenting the temporary flow reversal and unusual water chemistry, but my supervisors suggested that equipment malfunction was the most likely explanation. Conductivity meters can give false readings if they're not properly calibrated, and compass readings can be affected by magnetic interference from metal objects. But I know what I saw and measured at Beaver Creek that September morning. A stream flowing against gravity, carrying dissolved minerals from a dried-up creek 200 miles away. Water that contained chemical signatures from geology that doesn't exist in the Adirondack region. I've been back to the site 6 times since then, always hoping to find some explanation for what I observed. The creek flows normally now, carrying the same low mineral water it's carried for thousands of years. But sometimes, when I'm taking samples from other streams in the region, I think about that morning when physics stopped working at Beaver Creek. The thing that bothers me most isn't the flow reversal itself, although that was impossible enough. It's the chemical analysis that showed water from Cannonsville Creek flowing through Beaver Creek 3 years after Cannonsville had dried up completely. Where had that water been for 3 years? How had it traveled 200 miles through solid bedrock from one watershed to another? And why had it chosen that particular morning to flow backward through a stream that had followed the same path since the last ice age? I still have the water samples from that day, stored in our laboratory freezer and preserved for future analysis. Sometimes I take them out and run additional tests, looking for clues I might have missed. The chemical signature is unmistakable water from the Catskill Mountains, flowing through an Adirondack stream that had somehow reversed its direction overnight. I don't know what caused Beaver Creek to flow backward, or how it came to carry water from a distant, dried-up watershed. But I'm certain of one thing: somewhere in the complex network of underground aquifers and rock fractures that connect all water systems, The normal rules of hydrology had temporarily stopped working, and I have the disturbing feeling that it's still happening in places where no one is there to notice or measure or document the impossible. My name is Amy Zhao, and I've been a paleontologist with the Smithsonian National Museum of Natural History for 12 years. I specialize in Carboniferous period fossils, particularly plant and invertebrate specimens from the coal-forming swamps that covered much of North America 300 million years ago. It's meticulous work, documenting ancient life forms that existed long before dinosaurs, long before anything resembling modern ecosystems. I thought I understood the timeline of life on Earth, the careful progression from simple organisms to complex ones, the millions of years that separate us from our most distant ancestors. I was wrong about all of it. In October of 2023, I was leading a collecting expedition in the coal country of southern West Virginia, specifically the Kanawha Formation exposures near the New River Gorge. This area is famous among paleontologists for its exceptional preservation of Carboniferous fossils, fern fronds, seed plants, primitive arthropods, and occasionally vertebrate remains from the earliest land animals. I was working with 2 graduate students, documenting a newly exposed section of shale, where recent erosion had revealed fresh, fossil-bearing layers. The exposures were textbook examples of Carboniferous stratigraphy, alternating bands of sandstone, shale, and coal seams laid down in ancient river deltas and swamp environments. The weather that week was perfect for fieldwork. Clear skies, temperatures in the 60s, no rain to make the exposed rock faces slippery or dangerous. We'd set up base camp in a small clearing about half a mile from the main fossil site, planning to spend 4 days systematically collecting and documenting specimens. On Tuesday morning, I was working a particularly promising layer of fine-grained shale, about 40 feet up a steep outcrop face. This type of sediment preserves fossils with exceptional detail, capturing even the delicate structure of leaves and the segmented bodies of ancient insects. I was using standard collecting techniques, carefully splitting the shale along natural bedding planes, photographing each layer before removing specimens, documenting the precise stratigraphic position of every find. That's when I cut my hand. I was using a geology pick to carefully split a piece of shale when the tool slipped and caught the side of my left index finger. Not a serious injury, just a clean slice about half an inch long that bled more than it should have. I cleaned the wound with antiseptic from our field kit and covered it with a bandage, the kind of minor accident that happens regularly during fieldwork. The cut left a distinctive scar, a straight line running diagonally across the outer edge of my index finger, just below the first joint. I made a mental note to be more careful with the tools, especially when working on unstable rock faces. We spent the rest of Tuesday and all of Wednesday collecting specimens from different layers of the outcrop: standard Carboniferous fauna trilobites, brachiopods, crinoid stems, beautifully preserved fern fossils. Everything was exactly what you'd expect to find in 300 million year old sediments from the late Paleozoic era. Thursday morning, I was working a different section of the outcrop, about 20 feet to the east of where I'd cut my finger 2 days earlier. The rock was similar fine-grained shale with excellent preservation potential, but this layer seemed to contain fewer fossils than the others we'd been working. I was carefully splitting a large piece of shale when I found something that shouldn't have existed. Pressed into the rock surface was what appeared to be a human handprint, not the hand bones of some ancient primate, an actual handprint, as if someone had pressed their palm into soft mud that had then hardened into stone over millions of years. The preservation was perfect. I could see the fine details of palm lines, the individual ridges and valleys of fingerprints, even what looked like fabric impressions around the wrist area. The print was preserved in negative relief, forming a natural mold in the ancient sediment. But humans didn't exist 300 million years ago. The earliest human ancestors wouldn't appear for another 290 million years. In the Carboniferous period, the most advanced land vertebrates were primitive amphibians and early reptiles. Nothing with hands that looked remotely human. I photographed the specimen from multiple angles, recorded its exact stratigraphic position, and called my graduate students over to document the find. Sarah Chen and Michael Rodriguez had been working with me for 2 years, and they knew enough about Carboniferous paleontology to recognize the impossibility of what we were looking at. Dr. Zhao, that's definitely a human handprint, Sarah said, studying the fossil through a magnifying lens. But it can't be. The rock layers here are Pennsylvanian age, late Carboniferous. Nothing with human-like hands existed then. I knew she was right. The stratigraphy of the site was well established. We were working in sediments that had been laid down 300 million years ago, during a time when the most advanced life forms on land were primitive forests of giant ferns and early seed plants. But the evidence was right there in the rock, preserved with the same exceptional detail as the fern fossils we'd been collecting all week. I spent the afternoon taking detailed measurements of the handprint, comparing it to the size and proportions of modern human hands. The print measured 7 3/4 inches from wrist to fingertip, with finger lengths and palm width consistent with an adult human hand. That evening at our base camp, I uploaded the photographs to my laptop and began a more detailed analysis. I measured the finger lengths, calculated the ratios between different hand segments, and compared the proportions to databases of human hand measurements. The handprint matched my own hand exactly. Same overall size, same finger length ratios, same palm width and finger spacing. When I held my left hand up to the computer screen and compared it to the fossil photograph, the match was perfect. Every measurement, every proportion, every detail of bone structure aligned with mathematical precision. But that wasn't the most disturbing part. When I examined the high-resolution photographs more carefully, I could see a distinctive mark on the index finger of the fossilized handprint, a straight diagonal line, about 1/2 inch long, running across the outer edge of the finger just below the first joint. The same scar I'd gotten 2 days earlier when my geology pick slipped while collecting specimens from this same outcrop. I stared at the photographs for over an hour, checking and rechecking the measurements, comparing the scar patterns, looking for any explanation that made sense. There was no doubt the fossilized handprint was identical to my own hand, complete with a scar that hadn't existed until Tuesday morning. I called Dr. Robert Martinez at the Smithsonian, my department supervisor and one of the leading experts on Carboniferous paleontology. Dr. Martinez has been studying 300-million-year-old fossils for 30 years. And if anyone could explain what I'd found, it would be him. Amy, that's impossible, he said when I described the handprint and sent him the photographs. You know as well as I do that human ancestors didn't exist in the Carboniferous. And even if they did, the preservation of soft tissue details like fingerprints is extremely rare in rocks that old. I sent him the detailed measurements and comparison photographs showing the match to my own hand. He called me back the next morning, sounding puzzled and concerned. I've reviewed your documentation, and I can't explain it, he admitted. The stratigraphy is clearly Carboniferous age, but the handprint is definitely modern human. There's no geological process that could account for a recent impression, appearing in 300-million-year-old rock. We spent Friday carefully extracting the handprint specimen and preparing it for transport back to the Smithsonian laboratories. I wanted to conduct radiometric dating on the surrounding rock matrix, chemical analysis of the fossil surface, and microscopic examination of the preservation details. But when we reached the outcrop that morning, we found that the section containing the handprint had collapsed overnight. A large portion of the rock face had broken away and tumbled down the slope, taking the fossil site with it. We spent hours searching through the rubble, but the handprint specimen was gone, buried under tons of broken shale and sandstone. The official expedition report documented our other fossil finds, the fern fronds, trilobites, and other Carboniferous specimens we'd collected during the week. There was no mention of the impossible handprint, no record of the photographs I'd taken, no documentation of the measurements that matched my own hand perfectly. Dr. Martinez suggested that the handprint had probably been a natural formation mineral precipitation or sedimentary structures that resembled biological features. He pointed out that pareidolia, the tendency to see familiar patterns in random formations, was common in paleontological fieldwork. But I still have the photographs on my personal camera, stored on multiple backup drives and preserved in my private research files. The images clearly show a perfect human handprint, preserved in 300-million-year-old rock, complete with fingerprint details and a scar that matched my own injury from 2 days earlier. I've been back to the site twice since then, always on my own time. The outcrop face is still partially collapsed, but new erosion has exposed fresh rock layers. I've found typical Carboniferous fossils, plants, invertebrates, early vertebrate remains, but nothing that challenges the established timeline of life on Earth. The thing that haunts me most isn't the impossibility of finding a human handprint in Carboniferous rock. It's the precision of the match to my own hand, including a scar that didn't exist until I cut myself while working at that exact location. Somehow, my handprint had been preserved in rock that formed 300 million years before I was born, complete with an injury I wouldn't receive until the day I discovered it. The timeline doesn't work. The geology doesn't work. The entire sequence of events violates everything we know about how fossilization occurs and how time moves forward. I don't know how my handprint ended up in 300-million-year-old rock, or why it included details from a future injury that hadn't happened yet when the sediments were deposited. But I'm certain of one thing: somewhere in the complex relationship between time and stone and the marks we leave behind, the normal rules of cause and effect had stopped working. And I have the terrible feeling that it's still happening, in layers of rock where past and future converge in ways we're not supposed to understand. My name is Kevin Sullivan, and I've been a geological survey technician with the Colorado Geological Survey for 17 years. Most of that time has been spent monitoring seismic activity in the Rocky Mountain region, setting up instruments to detect earthquakes, landslides, and other ground movement that could affect public safety. It's quiet work, mostly automated these days, but someone still needs to maintain the equipment and analyze the data. I thought I understood how the Earth moves, how seismic waves propagate through rock, how to distinguish natural geological processes from human-caused vibrations. I was wrong about the relationship between all of those things. In June of 2022, I was assigned to install a new seismograph station near Wildflower Campground in the San Juan National Forest, about 30 miles northeast of Durango. The campground sits in a glacial valley, surrounded by peaks over 12,000 feet high, and the area has a history of minor seismic activity associated with the Rio Grande Rift system. The installation was routine work: dig a concrete pad, set up the seismograph in a weatherproof enclosure, run power and data cables, calibrate the instruments. The device would monitor ground movement continuously, transmitting data back to our office in Denver via satellite link. Wildflower Campground is a popular destination during the summer months, with about 40 campsites scattered through a mixed forest of aspen and spruce. The elevation is 9,500 feet, high enough to stay cool even in July and August. Beautiful place for camping, with clear mountain streams and hiking trails that lead up to alpine lakes and 13,000-foot peaks. I finished the installation on a Wednesday afternoon in mid-June and ran initial tests to make sure everything was working properly. The seismograph was detecting normal background vibrations, small tremors from distant earthquakes, minor ground movement from thermal expansion and contraction, the kind of subtle activity that happens constantly in any geologically active region. The first unusual reading came that night at 3:17 a.m. The seismograph recorded a series of small tremors lasting about 90 seconds, not strong enough to be felt by humans, but clearly detectable by sensitive instruments. The vibrations had an unusual signature rhythmic pulses, rather than the random patterns you typically see from natural seismic events. I assumed it was equipment noise or interference from the campground's electrical systems. Seismographs are sensitive to all kinds of artificial vibrations, generators, vehicles, even people walking near the instrument. I made a note to check the installation when I returned the following week, but when I downloaded the data 7 days later, I found that the same pattern had occurred every night at exactly 3:17 a.m. 90 seconds of rhythmic tremors, always starting and stopping at precisely the same times. The timing was too regular to be natural. Earthquakes don't follow schedules, and thermal expansion occurs gradually throughout the day and night. The vibrations looked artificial, but there was no obvious source for regularly occurring mechanical activity at the campground. I spent that afternoon walking around the area, looking for anything that might generate vibrations at 3:17 a.m. Water pumps, electrical equipment, automated systems that might cycle on and off during the night. I found nothing that could account for the seismic signals. The campground host, a retired teacher named Margaret Chen, had been working there for 5 summers. When I asked her about unusual activity during the night, she shook her head. "It's quiet here after about 10 p.m., she told me. "Most people go to bed early when they're camping. I've never noticed anything happening at 3 in the morning." I explained about the seismic readings and asked if she'd heard any mechanical noise or vibrations during the night. "No, nothing like that," Margaret said. "But you know, we do have people go missing sometimes. Usually, they just wander off trail and get found a day or two later. But occasionally, someone disappears completely." She mentioned a hiker who had vanished the previous summer, an experienced backpacker who had been camping alone in Site 23. His tent and gear were found undisturbed the next morning, but David Morrison was never seen again. Search and rescue had spent a week combing the area, with no results. I filed the conversation away as background information and focused on the seismic data. The pattern continued every night, precisely timed tremors that didn't match any known geological process. 2 weeks later, I expanded my investigation by checking historical data from a temporary seismograph that had been installed in the area during the summer of 2007. The old instrument had been part of a research project studying tectonic activity along the Rio Grande Rift, and the data was archived in our Denver office. What I found disturbed me more than the current readings. The same pattern appeared in the 2007 data, nightly tremors at 3:17 a.m., but only during the months when Wildflower Campground was open to the public. During the off-season, when the campground was closed and snow-covered, the seismic activity stopped completely. I went back further, requesting archived data from temporary monitoring stations that had operated in the area over the past 15 years. Every time we'd had seismographic coverage of the Wildflower Campground area, the same pattern appeared. Regular tremors during camping season, complete silence during winter months. But the most disturbing correlation came when I cross-referenced the seismic data with missing persons reports from the San Juan National Forest. I spent 3 days at the county sheriff's office, going through files of people who had disappeared in the area over the past 15 years. Hikers, campers, hunters, who had simply vanished without explanation. Most were found eventually, but 7 cases remained open. People who had disappeared completely, leaving behind no trace of what had happened to them. Every single unsolved disappearance had occurred during periods when our seismographs were recording the nightly tremor pattern. David Morrison, the backpacker who vanished in 2021. Jennifer Walsh, a geology student who disappeared while camping with friends in 2018. Michael Chen, a park ranger who went missing during a routine patrol in 2015. The correlation was perfect. Seismic activity coinciding with people who never came home. I presented my findings to Dr. Sarah Martinez, the state seismologist and my direct supervisor. Sarah has been studying Colorado earthquakes for 23 years, and if anyone could explain the pattern, it would be her. "Kevin, this is very unusual," she said after reviewing my data analysis. "The regularity suggests an artificial source, but I can't think of any mechanical system that would operate on such a precise schedule for 15 years. She paused, studying the correlation with missing persons cases. And the timing with disappearances is probably coincidental. People go missing in the mountains for all kinds of reasons: hypothermia, falls, getting lost. The seismic activity is more likely related to groundwater movement or thermal cycles in the bedrock. But I knew the correlation wasn't coincidental. 7 people had vanished from the Wildflower Campground area during 15 years of intermittent seismic monitoring. And every disappearance had occurred when our instruments were detecting the nightly tremor pattern. I returned to the campground in late July to install additional monitoring equipment. I wanted to triangulate the exact source of the vibrations using multiple seismographs positioned around the area. That's when I met James Park, a camper who had been staying at Site 18 for 3 nights. James was a geology professor from Colorado State University, and he'd been hearing unusual sounds during the night. "It's probably nothing," he told me as I was setting up the second seismograph. "But around 3 a.m. each night, I hear this low, rumbling sound. Not loud enough to wake most people, but it's definitely there. Seems to be coming from underground." I asked him to describe the sound in more detail. "Rhythmic, like machinery operating somewhere beneath the campground. Lasts for about a minute and a half, then stops. Very regular, very precise timing." James had been camping in the mountains for 20 years, and he'd never heard anything like it. He was planning to leave the next morning, but he offered to stay up that night and help me document whatever was causing the sounds and vibrations. We positioned ourselves near the central seismograph at 2:30 a.m. and waited. The forest was completely quiet, no wind, no animal sounds, just the normal silence of a mountain night. At exactly 3:17 a.m., the tremors began. I could feel them through the ground, subtle vibrations that seemed to pulse in a regular rhythm. James pointed toward the center of the campground, where the sounds appeared to be strongest. "There," he whispered. "Underground, maybe 20 or 30 feet down." The seismograph confirmed what we were feeling. Rhythmic pulses lasting exactly 90 seconds. Then complete silence. The vibrations were definitely coming from beneath the campground, but there was no visible source, no explanation for what might be generating such regular mechanical activity deep underground. James left the next morning as planned. 2 days later, Margaret Chen called to report that he'd never made it home to Fort Collins. His car was found in the campground parking lot with all his gear still inside. But James Park had simply vanished. The search and rescue operation lasted 6 days. They found no trace of him anywhere in the area, no footprints, no clothing, no sign that he'd ever left his campsite. The case was classified as a missing person incident, and the file was added to the growing collection of unsolved disappearances associated with Wildflower Campground. I submitted a detailed report documenting the correlation between seismic activity and missing persons cases. But the official response was that the data was interesting but not conclusive. Coincidences happen, and people disappear in the wilderness for many reasons that have nothing to do with underground vibrations. The seismograph continues to operate at Wildflower Campground, recording the same pattern every summer night. Regular tremors at 3:17 a.m., lasting exactly 90 seconds, stopping completely when the campground closes for winter. I've been back to the site 8 times since James Park disappeared, always during the camping season, always hoping to find some explanation for what's happening 20 feet beneath the forest floor. The tremors continue with mechanical precision, unchanged by weather or seasonal conditions, or the number of people camping in the area. But I've started noticing something else in the data that disturbs me even more than the regular pattern. The vibrations are getting stronger each year. Not dramatically stronger, but there's a measurable increase in amplitude from season to season. Whatever's causing the tremors is becoming more active, more powerful, more noticeable to sensitive instruments. I don't know what's operating beneath Wildflower Campground, or why it only functions when people are camping in the area. But I'm certain of one thing: 8 people have disappeared from that valley over the past 15 years, and every single disappearance occurred during periods when something underground was marking time with mechanical precision. And I have the terrible feeling that whatever's down there is still counting, still waiting, still following a schedule that no one understands, but everyone who camps there eventually becomes part of. My name is Rachel Kim, and I've been a research mineralogist with the Oregon Department of Geology and Mineral Industries for 15 years. I specialize in analyzing rock and mineral samples from landslides, mining sites, and geological surveys throughout the Pacific Northwest. I know the mineral composition of Oregon geology better than most people know their own neighborhoods. The common feldspars and quartz, the regional variations in volcanic glass, the trace elements that tell the story of how rocks formed. I thought I understood what minerals could exist in this part of the world, what elements occur naturally in Pacific Northwest geology, what combinations are possible given our regional geological history. I was wrong about the relationship between observation and reality. In March of 2023, I was called to analyze rock samples from a large landslide near the town of Government Camp on Mount Hood. Heavy spring rains had destabilized a slope along Highway 26, sending several thousand tons of rock and debris across the roadway. The Oregon Department of Transportation needed a geological assessment to determine if the area was safe for cleanup operations. The landslide site was typical for the Cascade Range volcanic rocks and sediments deposited over millions of years, weakened by groundwater and weathering processes. Mount Hood is an active volcano, and the entire region is built from layers of lava flows, ash deposits, and debris from ancient eruptions. I collected samples from different parts of the debris field, following standard procedures for post-landslide geological analysis. The rocks appeared normal, mostly andesite and dacite volcanic rocks, with some older sedimentary formations mixed in. Nothing unusual about the visual characteristics or the geological context. But when I began laboratory analysis back in Portland, I found something that shouldn't have existed. Every sample contained significant concentrations of rare earth elements that don't occur naturally in Cascade Range geology. Neodymium, europium, terbium, ytterbium, elements that are typically found in specialized geological environments like alkaline igneous complexes or rare earth ore deposits. The Pacific Northwest doesn't have the right geological conditions for these elements to occur in significant concentrations. Our volcanic rocks are relatively simple in composition, dominated by common silicate minerals and trace amounts of more typical elements like titanium and chromium. I ran the analysis 3 times using different instruments and sample preparation techniques. The results were consistent. Every rock sample from the Mount Hood landslide contained identical concentrations of rare earth elements that had no business being there. The mineral assemblage was even more puzzling. The rare earth elements were incorporated into crystal structures that I didn't recognize, forming compounds that didn't match any known mineral species. The chemical compositions were precise and consistent across all samples, but they didn't correspond to anything in the mineralogical literature. I photographed the samples under high magnification and documented the unusual mineral phases with our scanning electron microscope. The images showed perfect crystal formations with complex internal structures, but the chemical analysis indicated compositions that shouldn't have been stable under normal geological conditions. I called Dr. Michael Chen at the University of Oregon, a colleague who specializes in volcanic petrology and has studied Cascade Range rocks for over 20 years. Michael has analyzed thousands of samples from Mount Hood and the surrounding area, and if anyone could explain the unusual mineral assemblage, it would be him. "Rachel, that's impossible," he said when I described the rare earth element concentrations. "The magma chemistry at Mount Hood doesn't support the formation of rare earth minerals. The volcanic rocks there are depleted in those elements, not enriched." I sent him digital copies of my analytical data and microscope photographs. He called me back 2 days later, sounding puzzled and concerned. "I've reviewed your data, and I have to say it's remarkable," he admitted. "But I'd like to verify the results with independent analysis. Can you send me some of the actual rock samples?" I packaged 6 representative samples and sent them to Dr. Chen's laboratory at the University of Oregon. I also sent duplicate samples to Dr. Lisa Martinez at Oregon State University and Dr. Axis James Park at the United States Geological Survey in Menlo Park, California. 3 independent laboratories, 3 different analytical techniques, 3 opportunities to confirm or refute my findings. The results came back over the following 2 weeks, and they were more disturbing than I could have imagined. All 3 laboratories reported that my samples contained only common granite, standard mineral compositions dominated by quartz, feldspar, and biotite mica. No rare earth elements, no unusual mineral phases, no exotic crystal structures, just ordinary igneous rock of the type found throughout the western United States. Dr. Chen called me personally to discuss the discrepancy. Rachel, I've analyzed your samples with our best instruments, and I'm seeing normal granite composition, he said. Are you sure these came from the Mount Hood landslide? The mineral assemblage doesn't match anything from that area. I checked and rechecked my sample labels and chain of custody documentation. The rocks had definitely come from the government camp landslide site, and I'd followed proper procedures for collection and storage. But when I reanalyzed my original samples in our Portland laboratory, I got the same results as before: high concentrations of rare earth elements in unusual mineral phases that didn't exist in any geological reference. I spent the next week conducting additional tests, trying to understand why my instruments were detecting minerals that other laboratories couldn't find. I calibrated and recalibrated the analytical equipment, ran standard reference materials to check for systematic errors, and consulted with our senior geochemist about possible sources of analytical artifacts. Everything checked out. My instruments were working properly, my analytical techniques were sound, and my sample preparation methods were standard for the industry. But somehow, I was consistently detecting minerals that other scientists couldn't see. Dr. Sarah Foster, our department director and a mineralogist with 30 years of experience, reviewed my analytical protocols and quality control procedures. Rachel, your work is technically excellent, she told me after spending a day going through my laboratory notebooks. But if 3 independent laboratories are reporting different results from the same samples, we need to understand why. She suggested that I might be dealing with sample contamination or analytical interference from unknown sources. Sometimes, laboratory reagents or sample containers can introduce trace elements that appear to be part of the rock composition. But contamination doesn't explain why I was seeing complex mineral structures under the electron microscope, or why the rare earth element patterns were so consistent across samples collected from different parts of the landslide site. I returned to the Mount Hood area and collected additional samples, following even more rigorous procedures to prevent contamination. I used new sample containers, different collection tools, and documented every step of the process with photographs and GPS coordinates. The new samples showed exactly the same mineral compositions as the original ones. Identical rare earth element concentrations, identical crystal structures, identical chemical signatures that shouldn't have existed in Cascade Range volcanic rocks. I sent the new samples to 5 different laboratories across the country, including some of the most prestigious analytical facilities in North America. Every single laboratory reported that my samples contained only common granite. But in my laboratory, using my instruments, the rare earth minerals were clearly visible and consistently detectable. Dr. Foster called a meeting with our senior staff to discuss what she termed the Mount Hood anomaly. The consensus was that I was dealing with some kind of systematic analytical error that was affecting only our laboratory instruments. Rachel, I think you need to step back from this project. Dr. Foster told me privately after the meeting. Something is interfering with your analytical results, and until we can identify the source of the problem, we can't rely on data from your laboratory. I was reassigned to other projects, and the Mount Hood landslide samples were sent to external laboratories for independent analysis. The official geological report classified the landslide as a normal slope failure involving typical Cascade Range volcanic rocks. but I still have the original samples in my personal research collection, stored in a locked cabinet in my home office. When I analyze them with portable instruments, I still detect the same rare earth mineral assemblages that other laboratories can't see. I've been back to the Mount Hood landslide site 4 times since then, always on my own time. The area has been stabilized and the highway reopened, but I can still collect small samples from the debris field. Every sample I collect shows the same impossible mineral composition when I analyze it personally. But every time I send samples to other laboratories, they report only common granite. The thing that disturbs me most isn't the analytical discrepancy itself, although that's troubling enough. It's the precision and consistency of the rare earth mineral assemblages that only I can detect. The crystal structures are perfectly formed, the chemical compositions are exactly repeatable, and the element patterns suggest geological processes that don't occur in volcanic environments. It's as if there's an entire parallel mineral world that exists only when I'm observing it, complete with complex chemistry and crystal structures that follow their own rules of formation and stability. I don't know why my instruments consistently detect minerals that other laboratories can't find, or what geological processes could have created such exotic rare earth assemblages in ordinary volcanic rocks. But I'm certain of one thing: the Mount Hood landslide contained minerals that exist only for me, following laws of chemistry and crystal formation that operate outside the normal scientific framework. And I have the terrible feeling that I'm seeing evidence of geology that exists in a dimension other scientists can't access, where elements and minerals behave according to principles we're not supposed to understand. My name is David Torres, and I've been a land survey geologist with the Alaska Department of Natural Resources for 21 years. Most of that time has been spent mapping remote areas of the state for mineral potential, land use planning, and environmental assessment. I know how to read topographic maps, how to use GPS equipment in challenging terrain, and how to navigate through some of the most isolated wilderness in North America. I thought I understood how navigation works, how coordinates translate to physical locations, how geological formations remain stable over time. I was wrong about the relationship between all of those things. In August of 2023, I was assigned to conduct a geological survey of unmapped terrain in the northern section of Denali National Park. The area was about 60 miles from the nearest road, accessible only by helicopter or a multi-day hike through trackless wilderness. My job was to map the geological formations, collect rock samples, and assess the mineral potential of approximately 50 square miles of subarctic tundra and forest. The helicopter dropped me at a base camp on a Tuesday morning, along with enough supplies for 2 weeks of independent fieldwork. The weather was perfect for the job: clear skies, temperature in the 60s, no wind to speak of. I had GPS coordinates for 12 predetermined survey points distributed across the study area, plus the flexibility to investigate any interesting geological features I encountered. The landscape was typical interior Alaska rolling hills, covered with spruce and birch forest, interspersed with open meadows and boggy areas. The bedrock geology was complex, with metamorphic rocks from ancient mountain-building events mixed with more recent volcanic deposits. Exactly the kind of terrain that requires careful mapping and systematic sampling. I spent the first 3 days working the southern section of the study area, hiking between survey points and documenting the geological formations. Everything was proceeding normally. The GPS coordinates led me to the correct locations. The rock formations matched what I expected from regional geological maps, and my sampling was on schedule. On Friday morning, I set out for Survey Point 7, located about 5 miles northeast of my base camp. According to the GPS coordinates, the point was in a small clearing surrounded by mature spruce forest at an elevation of about 2,200 feet. I followed a compass bearing from my camp, using the GPS unit to navigate through dense forest and across several small streams. The hike took about 2 hours, and I arrived at the coordinates right on schedule. The clearing was exactly as described in the survey plan, about 40 feet across, roughly circular, with scattered boulders and low vegetation. I set up my equipment and began documenting the geological features, taking rock samples and photographs according to standard procedures. The bedrock was interesting gneiss and schist formations that suggested high-grade metamorphism, probably related to ancient tectonic activity. I collected samples from several outcrops and recorded detailed notes on the mineral composition and structural orientation of the rocks. After completing the work at Survey Point 7, I hiked northwest toward Point 8, following GPS coordinates and compass bearings through several miles of similar terrain. The navigation was straightforward, and I reached the destination without any problem. But when I arrived at the coordinates for Survey Point 8, I found myself in the same clearing I'd just left. I checked my GPS unit multiple times, verified the coordinates, and confirmed that I was following the correct route. According to the instruments, I was at Survey Point 8, about 3 miles northwest of Point 7, but I was standing in the identical clearing, looking at the same boulders and vegetation patterns I'd documented 2 hours earlier. I assumed I'd made a navigation error, despite the GPS readings showing the correct coordinates. It's easy to get turned around in dense forest, and GPS units can sometimes give false readings near large rock formations or in areas with unusual magnetic properties. I hiked back to my base camp and double-checked my route planning. The coordinates for survey points 7 and 8 were definitely different, and the planned routes between them should have taken me through distinct terrain features. But somehow, I'd ended up in the same location twice. The next morning, I decided to approach Survey Point 8 from a completely different direction. Instead of hiking northwest from Point 7, I would start from my base camp and follow a direct route to the coordinates. I used a different GPS unit, checked my compass bearings against multiple landmarks, and followed a path that took me through terrain I hadn't covered the previous day. The hike took about 3 hours, crossing a ridge and several stream valleys that were definitely not part of Friday's route. But when I reached the coordinates for Survey Point 8, I was back in the same clearing. The rock formations, the vegetation patterns, the scattered boulders, everything was identical to what I'd found at Survey Point 7. I was certain I hadn't been to this location before during Saturday's hike, but the geographical features were unmistakably the same. I spent the afternoon conducting a more detailed geological survey of the clearing, trying to understand what was causing the apparent coordinate confusion. I took additional rock samples, mapped the boulder distribution, and documented every geological feature with photographs and GPS measurement. That's when I noticed something disturbing. The rock samples I collected on Saturday showed slightly different mineral compositions from those I'd taken on Friday. The gneiss formations contained different proportions of quartz and feldspar, and the schist layers showed variations in metamorphic grade that shouldn't have existed at the same location. Geological formations don't change composition over a period of 24 hours. Rock chemistry is stable over thousands or millions of years, and mineral assemblages remain constant unless affected by major geological processes like volcanism or extreme metamorphism. I compared the rock samples side by side under my field microscope. They were definitely from the same general rock types, but the detailed mineralogy was different in ways that couldn't be explained by normal geological variation. On Sunday, I decided to test my navigation system more rigorously. I would hike to 3 different survey points using completely independent routes, documenting every step of the journey with GPS waypoints and compass bearings. I started with Survey Point 9, located about 4 miles southwest of my base camp. The route took me through boggy terrain and across a significant stream, following landmarks that were completely different from my previous hikes. After 2.5 hours of careful navigation, I arrived at Survey Point 9. It was the same clearing. The coordinates on my GPS unit showed the correct numbers for Point 9, but I was standing in the identical location I'd visited on Friday and Saturday. Same boulders, same vegetation, same general layout of geological features. But when I examined the rock formations, I found they had changed again. The metamorphic grade was higher than what I'd observed on previous visits, with mineral assemblages that indicated more intense heat and pressure during formation. The structural orientation of the rock layers had also shifted, showing fold patterns that were different from my earlier measurements. I spent the rest of Sunday documenting the changes and trying to understand what was happening to the geology of this location. The clearing existed at multiple sets of GPS coordinates simultaneously, but the bedrock was slowly evolving in ways that violated fundamental principles of geological science. On Monday, I hiked to survey points 10, 11, and 12. Each route took me through different terrain, following different compass bearings, crossing different streams and ridges, but every GPS coordinate led me back to the same clearing. And each time I arrived, the geological formations had changed a little more. The rock types were becoming more exotic, showing mineral assemblages that didn't match regional geological maps. The metamorphic textures were evolving toward compositions that required extreme pressure and temperature conditions. The structural patterns were becoming more complex, with fold and fault systems that suggested tectonic forces far beyond what should have affected this area. By Wednesday, when the helicopter was scheduled to pick me up, I had visited the same clearing 8 times using 8 different sets of GPS coordinates. Each visit had revealed further changes in the bedrock geology, as if the entire geological column was slowly transforming from one rock type to another. I collected samples from each visit and labeled them according to the date and supposed coordinates. When I returned to our laboratory in Anchorage, I submitted them for detailed chemical and mineralogical analysis. The results confirmed what I'd observed in the field. The rock samples showed a systematic progression from typical regional metamorphic rocks to exotic high-pressure assemblages that shouldn't have existed anywhere in interior Alaska. My supervisor, Dr. Jennifer Walsh, reviewed my field notes and analytical data with considerable skepticism. "David, this is impossible," she said after spending an afternoon going through my documentation. "GPS coordinates don't lead to the same location when they're different numbers, and bedrock geology doesn't change over a period of days." She suggested that I'd probably experienced equipment malfunction combined with navigation errors, and that the apparent geological changes were the result of sampling different locations while thinking I was in the same place. But I know what I saw and measured during that week in Denali. The same clearing, accessed through 8 different sets of coordinates, with bedrock that was slowly transforming according to geological processes that operate over millions of years, not days. I've been back to the study area twice since then, always on my own time. I've tried to relocate the clearing using my original GPS coordinates, but I've never found it again. The survey points lead to normal geological formations that match the regional maps and show no signs of the exotic metamorphic assemblages I documented in 2023. The official survey report classified my work as inconclusive due to equipment malfunction and navigation errors. The area was marked for future resurveying when more reliable GPS technology becomes available. But I still have the rock samples from each visit to the clearing, stored in our laboratory collection and preserved for future analysis. The samples clearly show a progression from normal regional geology to impossible high-pressure mineral assemblages that shouldn't have existed in that location. I don't know why 8 different GPS coordinates led me to the same clearing, or how the bedrock geology could have changed so dramatically over the course of a week. But I'm certain of one thing. Somewhere in the vast wilderness of Denali National Park, there's a location that exists at multiple sets of coordinates simultaneously, where geological time moves faster than it should, and rocks transform according to rules that operate outside our understanding of how the Earth works. And I have the disturbing feeling that the clearing is still there, still changing, still accessible through coordinates that lead to impossible places, where navigation and geology follow different laws than the ones we use to map the world. My name is Jennifer Walsh, and I've been a geological engineer with the New Hampshire Department of Transportation for 18 years. Most of that work has involved foundation studies for bridges, road construction, and slope stability assessments throughout the White Mountain region. I know how drilling equipment behaves in different rock formations, how to interpret subsurface conditions from drilling resistance and core samples, and how to troubleshoot mechanical problems in the field. I thought I understood the relationship between drilling equipment and the rock it penetrates, how depth measurements correspond to actual penetration, how drill bits respond to different geological conditions. I was wrong about the nature of the space that exists beneath our feet. In September of 2023, I was conducting a foundation study for a proposed bridge replacement on Route 16 near Jackson, New Hampshire. The existing bridge crossed a small stream in a valley surrounded by the typical granite peaks and forested ridges of the White Mountain. Standard engineering work drill test holes to determine bedrock depth and bearing capacity. Collect core samples for laboratory analysis. Assess the geological conditions for foundation design. The drilling site was in a small clearing about 50 yards from the existing bridge, surrounded by mixed hardwood forest that was just beginning to show fall colors. The weather was perfect for the work. Clear skies, temperature in the 60s, no wind to interfere with the drilling operation. I was using a truck-mounted rotary drill rig, standard equipment for this type of subsurface investigation. The plan was to drill 3 test holes to a depth of about 50 feet, reaching bedrock and collecting continuous core samples to document the geological profile. The first 2 holes proceeded exactly as expected. I drilled through about 15 feet of glacial till and weathered rock, then hit solid granite bedrock, typical of the White Mountain region. The drilling was straightforward, consistent resistance, normal core recovery, predictable behavior from the equipment. I started the 3rd hole on Tuesday afternoon, following the same procedures I'd used for the previous 2 locations. The surface geology looked identical, and I expected to find the same soil and bedrock conditions. For the first 30 feet, everything was normal. The drill bit penetrated through glacial deposits and weathered granite, bringing up core samples that matched what I'd found at the other test locations. The drilling resistance was consistent with solid rock, and the equipment was operating smoothly. Then, at exactly 30 feet depth, the sound changed. The drilling rig went completely silent. Not the kind of silence you get when equipment shuts down. The engine was still running, the hydraulics were still operating, and the drill string was still rotating. But the characteristic sound of the drill bit cutting through rock had simply stopped. I've been operating drilling equipment for 18 years, and I know the acoustic signatures of different drilling conditions. Hard rock sounds different from soft rock, which sounds different from soil or weathered material. Complete silence means the drill bit isn't encountering any resistance at all. But my instruments showed that the drill was still penetrating solid rock. The torque readings indicated normal resistance. The hydraulic pressure was consistent with drilling through granite, and the depth meter was recording steady downward progress. I stopped the drilling operation and checked the equipment for mechanical problems. The drill string was rotating properly, the bit was sharp and undamaged, and all the hydraulic systems were functioning normally. There was no obvious reason for the change in acoustic behavior. I resumed drilling, advancing the bit slowly and monitoring all the instrument readings. The silence continued. No sound of metal cutting through rock, no vibration transmitted through the drill string, no acoustic feedback from the drilling process. But the depth meter kept recording downward progress, and the torque readings suggested the bit was working against normal rock resistance. At 50 feet depth, I stopped to collect a core sample. Standard procedure: pull the drill string up, remove the core barrel, examine the rock samples that should have been collected during the drilling process. The core barrel was empty. I'd been drilling for 20 feet through what the instruments indicated was solid granite bedrock, but I hadn't collected a single fragment of rock or soil. The core barrel was as clean as when I'd installed it. I checked the core barrel for mechanical problems, made sure the sample retention system was working properly, and ran the drill string back down the hole. At 50 feet, I resumed drilling into what should have been solid granite. The silence continued. No sound, no vibration, no core recovery. But the depth meter kept recording progress, and the hydraulic system kept working against resistance that felt like normal rock drilling. At 75 feet, I tried to collect another core sample. The barrel was still empty. At 100 feet, the same result. Clean core barrel. No rock fragments. No evidence that the drill bit was actually cutting through anything, despite the instrument readings that suggested normal drilling conditions. I called my supervisor, Mark Chen, on my cell phone and described what was happening with the drilling operation. "Jennifer, that's not possible," he said after I explained the situation. "If you're not getting core recovery, the bit isn't cutting rock. Check your depth measurements. You might have a malfunction with the depth counter." I checked and rechecked the depth measurement system. The mechanical counter was working properly, and I could verify the depth by measuring the length of drill string that had been fed into the hole. According to both methods, I drilled over 100 feet into solid rock without collecting a single sample. Mark told me to shut down the operation and return to the office. We'd review the equipment and try to understand what had gone wrong with the drilling system. But when I tried to pull the drill string out of the hole, I encountered a problem that disturbed me more than the silence and lack of core recovery. The depth meter showed that I drilled to 120 feet, but my drilling rig only carried 300 feet of drill pipe, and I'd used only about 30 feet of string to reach what should have been 120 feet depth. According to the depth counter, I'd somehow drilled 450 feet into the ground, using only 30 feet of physical drill pipe. I spent the next hour trying to reconcile the measurements. The mechanical depth counter, the electronic depth meter, and the hydraulic penetration sensors all indicated that the drill bit had reached 450 feet below ground surface, but I'd only fed 30 feet of drill string into the hole. When I finally pulled the drill string back to the surface, I found something that made the entire situation even more inexplicable. The drill bit was perfectly clean and sharp, showing no signs of wear or contact with rock. After supposedly drilling over 400 feet through granite bedrock, the cutting edges were as pristine as when I'd installed them that morning. I've operated drilling equipment in every kind of rock formation found in New Hampshire, and drill bits always show wear after extended use. Granite is particularly abrasive, and drilling 400 feet through solid granite should have significantly damaged the cutting surfaces. But this drill bit looked like it had never touched rock. I packed up the equipment and drove back to our office in Concord, trying to understand what had happened at the drilling site. The instrument readings clearly showed penetration to 450 feet, but the physical evidence suggested the drill bit had never cut through anything. Mark Chen reviewed my drilling logs and instrument data with considerable skepticism. "Jennifer, these readings don't make sense," he said after spending an afternoon going through the documentation. "You can't drill 450 feet with 30 feet of drill pipe, and you can't penetrate granite without getting core samples or bit wear." He suggested that I'd experienced multiple equipment malfunctions simultaneously, faulty depth measurement, core barrel problems, and instrument calibration errors. The combination of problems had created confusing data that didn't reflect actual drilling conditions. The official report classified the third test hole as inconclusive due to equipment malfunction. The bridge foundation design proceeded using data from the first two successful test holes, which showed normal geological conditions for the area. But I know what my instruments recorded during that drilling operation: 450 feet of penetration through solid rock, using only 30 feet of drill pipe, without collecting core samples or wearing down the drill bit. I've been back to the site 3 times since then, always on my own time. The test hole is still there, marked with a steel cap and survey monument. When I lower a weighted tape measure into the hole, it reaches bottom at exactly 30 feet, the normal depth, where bedrock would be expected in that area. But sometimes, when I'm operating drilling equipment at other sites in the White Mountains, I think about those silent hours when my drill bit was cutting through space that didn't behave according to normal physical laws. The thing that disturbs me most isn't the impossible depth readings or the lack of core recovery. It's the complete absence of sound when the drill bit was supposedly cutting through solid granite. Sound is created by mechanical interaction, metal striking rock, vibration transmitted through solid materials, the fundamental physics of drilling operations. Silence means there was no interaction at all. I don't know what my drill bit was penetrating during those 420 feet of impossible drilling, or how it managed to advance through space that existed beyond the physical length of my equipment. But I'm certain of one thing. Somewhere beneath that clearing in the White Mountains, there's a void that extends far deeper than our instruments can measure, filled with material that offers resistance without substance and depth without dimension. And I have the terrible feeling that the silence I heard that day was the sound of drilling through the fabric of space itself into regions where the normal rules of physics stop working, and drill bits can penetrate infinite distance without ever touching anything solid. My name is Mark Stevenson, and I've been a field researcher with the Montana Bureau of Mines and Geology for 14 years. Most of that time has been spent documenting geological features in remote areas of the state, mapping rock formations, cataloging mineral deposits, and photographing distinctive geological landmarks for our survey database. I know how to identify unique rock formations, how to distinguish one boulder from another, and how to document geological features with scientific precision. I thought I understood how large rocks behave over time, how glacial erratics remain stationary for thousands of years, how geological landmarks serve as permanent reference points in the landscape. I was wrong about the relationship between rocks and the space they occupy. In June of 2023, I began a 3-month survey of the Absaroka Beartooth Wilderness, documenting geological features across approximately 200 square miles of remote mountain terrain. The project was part of our ongoing effort to update geological maps and create a comprehensive database of significant rock formations in Montana's wilderness areas. The work involved systematic photography and GPS mapping of distinctive geological features, unusual rock formations, glacial erratics, prominent outcrops, and other landmarks that could serve as reference points for future geological studies. Standard fieldwork that I'd done dozens of times in different parts of the state. On my 3rd day in the field, I encountered a boulder that immediately caught my attention. It was a massive granite erratic, about 12 feet high and roughly spherical, sitting alone in a small meadow surrounded by pine and fir forest. The boulder was distinctive in several ways: an unusual pinkish color from feldspar crystals, a prominent quartz vein running diagonally across one face, and a unique pattern of orange and gray lichen covering about 30% of the surface. I photographed the boulder from multiple angles, recorded its GPS coordinates, and documented its geological characteristics in my field notebook. It was the kind of distinctive landmark that makes an ideal reference point easily recognizable, unlikely to be confused with other rock formations, and permanent enough to serve as a survey marker for decades. I labeled it Boulder 1 in my documentation system and continued with the survey work. 2 weeks later, while working an area about 8 miles northeast of the first location, I found the same boulder. At first, I assumed it was a similar rock formation. Glacial erratics often show comparable characteristics, especially when they're derived from the same geological source. But when I compared my photographs and field notes, the match was perfect. The size, the shape, the distinctive quartz vein, the exact pattern of lichen growth, everything was identical. I was looking at the same boulder I documented 2 weeks earlier, sitting in a different meadow 8 miles away from its original location. I checked my GPS coordinates multiple times and reviewed my field notes to make sure I hadn't made a navigation error. The coordinates were definitely different, and I'd approached this location from a completely different direction. This was a separate site, but the boulder was unmistakably the same. I photographed it again and compared the new images to my original documentation. The lichen patterns matched down to the smallest details. The weathering characteristics were identical. Even the way shadows fell across the granite surface showed the same topographical features. Large boulders don't move 8 miles across mountain terrain. Glacial erratics are deposited by ice sheets and remain in the same locations for thousands of years, unless moved by major geological events like landslides or earthquakes. There had been no seismic activity in the region, no evidence of recent geological disturbance. I spent the next month working different sections of the survey area, documenting dozens of other geological features. But every few days, I would encounter the same distinctive boulder in a new location. Third sighting, 12 miles southwest of the original site, in a rocky basin near a small alpine lake. Same size, same quartz vein, same lichen patterns. Fourth sighting, 15 miles northwest, on a ridge overlooking a deep valley, identical in every detail to the previous sightings. Fifth sighting, 6 miles due south of the original location, in a meadow that showed no signs of recent disturbance or heavy equipment access. By the end of July, I had photographed the same boulder in 8 different locations across a 30-mile stretch of wilderness. Each time, I documented the GPS coordinates, measured the boulder dimensions, and compared the lichen patterns to my previous photographs. The matches were perfect. Every sighting showed the same unique characteristics: the distinctive quartz vein, the particular coloration of the granite, the exact distribution of orange and gray lichen across the surface. I was tracking a 12-foot granite boulder that was somehow appearing in multiple locations across roadless wilderness terrain. I called Dr. Sarah Chen, my supervisor at the Bureau of Mines and Geology, and described what I was documenting during the survey. "Mark, that's not possible," she said after I explained the repeated sightings. "Boulders that size don't move without major geological events or human intervention. Are you sure you're not seeing similar rocks rather than the same rock?" I sent her digital copies of all my photographs and GPS data. She called me back 2 days later, sounding puzzled and concerned. "I've reviewed your documentation, and the lichen patterns are definitely identical," she admitted. "But there's no geological process that could account for a boulder moving that distance across mountain terrain." She suggested that I might be dealing with multiple boulders from the same glacial source, deposited during the last ice age, in a pattern that created similar weathering and lichen colonization. But even she seemed skeptical of that explanation when confronted with the photographic evidence. In August, I decided to conduct a more systematic investigation. Instead of just photographing the boulder when I encountered it, I would excavate around the base to determine how it was positioned relative to the underlying bedrock. When I found the boulder for the 9th time, in a location about 20 miles east of the original sighting, I spent a full day carefully digging around its base with a small trenching shovel. What I found disturbed me more than the impossible movement itself. The boulder wasn't sitting on top of the ground like a typical glacial erratic. It was embedded directly into solid bedrock, as if it had formed in place as part of the underlying geological formation. The granite composition of the boulder matched the bedrock perfectly, and there was no evidence of a contact zone between the erratic and the surrounding rock. Glacial erratics are foreign rocks deposited by ice sheets, compositionally different from the underlying bedrock. But this boulder appeared to be an integral part of the local geology, formed in place rather than transported from a distant source. I collected rock samples from both the boulder and the surrounding bedrock and sent them to our laboratory for chemical analysis. The results confirmed what I'd observed in the field: identical mineral composition, identical crystal structure, identical age dating. The boulder and the bedrock were the same rock formation. But that raised an even more disturbing question. If the boulder was part of the local bedrock, how could it appear in multiple locations across 50 miles of wilderness terrain? I found the boulder 4 more times during the final month of the survey, always embedded in bedrock, always showing the same impossible integration with the local geology. Each time, I excavated around the base and confirmed that it was formed in place rather than deposited by glacial action. By the end of September, I had documented the same distinctive boulder in 12 different locations across a 50-mile stretch of the Absaroka Beartooth Wilderness. Each location showed identical bedrock integration, identical mineral composition, and identical surface characteristics down to the finest details of lichen distribution. The official survey report classified my boulder documentation as anomalous geological features requiring further investigation. The repeated sightings were noted, but not explained, and the area was marked for follow-up study by a team of specialists. But when Dr. Chen returned to the survey area the following summer with additional researchers, they found only typical glacial erratics and bedrock formations. None of the GPS coordinates I'd recorded led to locations containing distinctive pink granite boulders with diagonal quartz veins. I've been back to the area twice since then, always on my own time. I've never found the boulder again, despite hiking to all 12 documented locations and searching the surrounding terrain. The photographs are still in our survey database, showing the same distinctive rock formation in multiple locations across roadless wilderness. But without the physical evidence, the documentation has been classified as a filing error or equipment malfunction that created false GPS coordinates. I know what I saw and documented during those 3 months in the Absaroka Beartooth Wilderness. The same boulder, appearing in 12 different locations, embedded in bedrock at each site, despite the geological impossibility of such formations. The thing that disturbs me most isn't the movement itself, although that defied every principle of geology I understand. It's the perfect integration with the bedrock at each location, as if the boulder had always been there, formed as part of the local geology millions of years ago. Rocks don't exist in multiple locations simultaneously. Geological formations don't appear and disappear according to who's observing them. Boulders don't embed themselves in bedrock and then move to new locations where they embed themselves again. But somewhere in the mountains of Montana, there's a distinctive granite boulder that exists in more places than it should, following rules of geology and physics that operate outside our understanding of how rocks and space and time work together. And I have the terrible feeling that it's still out there, still moving between locations according to patterns we can't predict, still embedding itself in bedrock that shouldn't be able to accommodate its presence, still following laws of existence that allow the same object to be in multiple places at once. My name is Patricia Olson, and I've been a topographical geologist with the United States Geological Survey for 22 years. Most of that time has been spent creating and updating elevation maps for remote areas of the American West, using precision instruments to measure the exact height and contour of mountain terrain. I know how elevation works, how topographic relationships define the shape of landscapes, and how to interpret the subtle variations that create accurate three-dimensional maps. I thought I understood the basic principles of geography, how valleys relate to peaks, how elevation measurements correspond to visual terrain features. I was wrong about the relationship between what we measure and what we see. In July of 2023, I was assigned to conduct a detailed topographic survey of the Sangre de Cristo Mountains in south-central Colorado. The project involved updating elevation data for approximately 100 square miles of wilderness terrain, using advanced GPS and barometric instruments to create high-resolution digital maps for the National Park Service. The work was routine but demanding hiking to predetermined survey points, taking precise elevation measurements, and documenting the three-dimensional structure of remote mountain terrain, the kind of systematic fieldwork I'd done dozens of times in different mountain ranges across the western United States. The Sangre de Cristo Range is typical high-altitude Rocky Mountain terrain. Sharp peaks rising above 14,000 feet, deep valleys carved by glacial action, complex topography that requires careful measurement and documentation. Beautiful country, but geographically challenging for precision survey work. I spent the first week establishing benchmark elevations at known survey points, calibrating my instruments against previously measured locations to ensure accuracy. The GPS and barometric altimeter readings matched the published elevation data within the expected margin of error, confirming that my equipment was working properly. During the second week, I began surveying unmapped areas in the northern section of the range. These were remote valleys and ridge systems that hadn't been accurately measured since the original topographic surveys of the 1930s and 40s. My job was to document the precise elevation and contour details for modern digital mapping systems. On Thursday morning, I hiked to a survey point in what appeared to be a typical mountain valley, surrounded by peaks rising to approximately 13,500 feet. The valley floor looked to be at about 11,000 feet elevation, based on the visual relationships with the surrounding terrain. Standard procedure: set up the GPS receiver, take barometric pressure readings, record the precise elevation at the survey point. I'd done this hundreds of times in similar terrain, and I expected to find elevations consistent with the visual geography. But when I checked my instruments, the readings didn't make sense. The GPS showed an elevation of 13,700 feet. The barometric altimeter confirmed the same reading. According to my precision instruments, I was standing at an elevation 200 feet higher than the surrounding mountain peaks. I assumed the instruments were malfunctioning, despite the successful calibration checks I'd completed earlier in the week. High-altitude conditions can sometimes interfere with GPS reception or barometric measurement, creating false readings that don't reflect actual elevation. I recalibrated both instruments using known benchmark data, checked the satellite reception quality, and repeated the measurements. The results were identical: 13,700 feet elevation, 200 feet higher than the peaks visible on all sides of the valley. Valleys don't exist at higher elevations than the mountains that surround them. It's a basic principle of geography, as fundamental as gravity itself. Water flows downhill, valleys form at lower elevations than peaks, and topographic relationships follow predictable patterns that have remained consistent for millions of years. I spent the afternoon taking additional measurements at different points across the valley floor. Every reading showed the same impossible elevation, consistently 200 feet higher than the surrounding peaks that I could see rising above me on all sides. I called Dr. Michael Chen, my supervisor at the USGS, on my satellite phone and described the contradictory elevation readings. "Patricia, that's impossible," he said after I explained the measurements. "Check your instrument calibration again. There might be atmospheric interference or equipment malfunction affecting the readings." I told him I'd already recalibrated multiple times and verified the measurements with 2 independent instruments. The elevation readings were consistent, but they contradicted the visual evidence of the valley's position relative to the surrounding terrain. "Are you sure you're in a valley?" he asked. "Maybe you're on a plateau or ridge that looks like a valley from your perspective." I looked around at the landscape surrounding my position. I was definitely in a valley depression, with steep mountainsides rising on all sides, and a small stream flowing downhill through the center of the depression. The visual geography was unambiguous. I was standing at the bottom of a mountain valley, not on a high plateau. Dr. Chen told me to continue with the survey and document all the elevation readings, regardless of whether they seemed consistent with the visual terrain. We'd analyze the data back at the office and try to understand what was causing the measurement discrepancies. I spent the next 2 days working other survey points in the area, but I kept thinking about the impossible elevation readings from the valley. Every principle of geography and topographic science said that valleys exist at lower elevations than the peaks around them. But my instruments were showing the exact opposite relationship. On Saturday, I returned to the valley with additional equipment, a different GPS unit, a second barometric altimeter, and a laser rangefinder that could measure relative elevations between different points. I wanted to verify the measurements with multiple independent instruments. The results were consistent across all equipment. The valley floor measured 13,700 feet elevation, while the surrounding peaks measured between 13,400 and 13,500 feet. According to every instrument I carried, I was standing in a valley that was 200 feet higher than the mountains around it. But the visual evidence contradicted the measurements completely. I was looking up at mountain peaks that rose clearly above my position, standing in a depression where water flowed downhill through the center of the valley. The landscape appeared exactly as a normal mountain valley should appear. I used the laser rangefinder to measure the relative elevation between my position and the visible mountain peaks. The instrument confirmed that the peaks were approximately 200 feet higher than my location, exactly what the visual terrain suggested. But when I checked the absolute elevation readings from GPS and barometric instruments, they showed that my position was 200 feet higher than the peaks. The relative measurements and absolute measurements were contradicting each other in ways that violated basic principles of geometry and physics. I spent Sunday documenting the contradictory measurements with photographs, GPS coordinates, and detailed instrument readings. I wanted to create a complete record of the impossible topographic relationships I was observing. The photographs clearly showed a typical mountain valley, with steep slopes rising on all sides and peaks visible above the valley floor. But the elevation data showed that the valley floor was higher than those peaks, creating a geographical impossibility that couldn't exist according to any known principles of topographic science. When I returned to our Denver office the following week, I presented my data to Dr. Chen and our senior cartographer, Dr. Lisa Martinez. They reviewed the elevation readings, examined the photographs, and tried to understand how the measurements could contradict the visual evidence so completely. "Patricia, these readings are definitely impossible, Dr. So," Martinez said after spending a day analyzing the data. "Valleys can't exist at higher elevations than surrounding peaks. There must be some systematic error in the measurement techniques or equipment." But they couldn't identify any problems with my methodology or instrument calibration. The GPS and barometric readings were consistent with each other and with measurements taken at other survey points in the region. Dr. Chen suggested that I might have encountered some kind of unusual atmospheric condition that affected the instrument readings while not affecting the visual appearance of the terrain. Temperature inversions or pressure anomalies can sometimes create false elevation readings, especially in complex mountain terrain. The official survey report classified the valley measurements as inconclusive due to unexplained instrument anomalies. The area was marked for future resurveying using different equipment and measurement techniques. But I've been back to that valley 3 times since then, always carrying multiple GPS units and barometric altimeters. Every visit produces the same impossible results: elevation readings that place the valley floor 200 feet higher than the surrounding peaks, despite visual evidence that clearly shows a normal topographic depression. I've also brought colleagues to the site, other topographic specialists who have reviewed my measurements and confirmed the instrument readings. Everyone agrees that the elevation data is impossible, but no one can explain why multiple independent instruments consistently produce the same contradictory results. The thing that disturbs me most isn't the impossible elevation readings themselves, although those violate every principle of geography I understand. It's the perfect consistency between what I see and what I measure, even though they contradict each other completely. My eyes show me a valley that exists below the surrounding peaks. My instruments show me a valley that exists above the surrounding peaks. Both sets of observations are internally consistent and apparently accurate, but they describe completely different topographic relationships for the same physical location. I don't know how a valley can simultaneously exist above and below the mountains that surround it, or how precision instruments can measure elevations that contradict visual evidence while remaining accurate according to all technical standards. But somewhere in the Sangre de Cristo Mountains, there's a valley that exists at 2 different elevations simultaneously, following laws of geography and physics that allow the same location to be both higher and lower than the terrain around it. And I have the terrible feeling that I've discovered a place where the normal rules of 3-dimensional space break down, where elevation becomes relative to the method of observation, where the same mountain valley can occupy multiple positions in vertical space, depending on whether you trust your eyes or your instruments. My name is Ryan Campbell, and I've been an environmental monitor with the National Park Service for 16 years. Most of that time has been spent working in Death Valley National Park, documenting temperature patterns, air quality, and climate conditions in one of the harshest environments in North America. I know how extreme heat behaves, how temperature variations affect desert ecosystems, and how to measure environmental conditions with scientific precision. I thought I understood the thermal dynamics of desert environments, how heat radiates from rock and sand, how temperature gradients create the characteristic patterns of arid landscapes. I was wrong about the relationship between heat and the ground beneath our feet. In August of 2023, I was conducting routine temperature monitoring in the Badwater Basin area of Death Valley, documenting the extreme heat conditions that make this region one of the hottest places on Earth. The assignment involved placing temperature sensors at predetermined locations across the valley floor, recording hourly readings throughout the summer heat season. The weather that August was typical for Death Valley daytime temperatures regularly exceeding 120 degrees Fahrenheit, with ground surface temperatures often reaching 160 degrees or higher. The kind of extreme heat that can kill unprepared visitors and creates thermal conditions unlike anywhere else in the United States. I'd been working the Badwater area for 8 years, and I knew the temperature patterns as well as anyone. The salt flats radiate heat like a giant reflector. The surrounding mountains trap hot air in the valley, and the below sea level elevation creates a natural furnace that concentrates thermal energy. On Tuesday morning, I was placing temperature sensors along a predetermined grid pattern when I encountered something that violated every principle of desert thermodynamics I understood. I found a perfectly circular area, about 10 feet in diameter, where the ground temperature was 32 degrees Fahrenheit. Not just cooler than the surrounding desert, actually, at the freezing point of water, in the middle of Death Valley, during a heat wave that was pushing ambient air temperatures above 120 degrees. I assumed my handheld thermometer was malfunctioning, despite the fact that it had been giving normal readings everywhere else. Extreme heat can sometimes interfere with electronic instruments, creating false readings that don't reflect actual conditions. I used a second thermometer to verify the reading, 32 degrees exactly, right at the surface of what appeared to be normal desert hardpan. The surrounding ground, just a few feet away, measured 158 degrees, hot enough to cause severe burns on contact. The boundary between the hot and cold areas was razor sharp. I could hold one hand over normal desert surface and feel the scorching heat, then move that same hand a few inches to the left and feel air that was barely above freezing. I marked the location with GPS coordinates and spent the afternoon documenting the temperature anomaly with multiple instruments. Every thermometer showed the same results, a perfect circle of 32 degree surface temperature surrounded by normal Death Valley heat. The cold spot showed no visual differences from the surrounding terrain. Same hardpan surface, same mineral deposits, same sparse vegetation around the edges, nothing that would suggest an underground water source, geothermal activity, or any other natural process that could account for the extreme temperature difference. I collected soil samples from inside and outside the cold circle and tested them with a field chemistry kit. Identical composition, the same salt-encrusted clay and mineral deposits found throughout the Badwater Basin. No unusual moisture content, no chemical differences that could explain the thermal anomaly. That evening, I called Dr. Jennifer Walsh, the park's chief scientist and my direct supervisor. Jennifer has been studying Death Valley's climate systems for 23 years, and if anyone could explain the temperature anomaly, it would be her. "Ryan, that's impossible," she said when I described the 32-degree readings. "There's no natural process that could create a localized cold spot like that in Death Valley summer conditions. Check your instruments again, you might have equipment malfunction." I told her I'd verified the readings with multiple thermometers and documented the exact boundaries of the affected area. The temperature differential was real, but I had no explanation for what could cause it. Jennifer told me to leave monitoring equipment at the site overnight and document any changes in the temperature pattern. We'd analyze the data, and try to understand what was causing the localized cooling effect. I set up 3 digital thermometers in different parts of the cold circle, programmed to record temperature readings every 15 minutes throughout the night. Standard environmental monitoring procedure, continuous data collection to identify patterns and understand the underlying processes. When I returned the next morning, the thermometers were gone, not scattered by wind or damaged by heat, completely missing from the site. I searched the surrounding area for over an hour, thinking they might have been moved by the rare wildlife that occasionally passes through Death Valley at night. I found no trace of the equipment anywhere near the monitoring site. But when I checked the temperature of the cold spot, it was still exactly 32 degrees Fahrenheit, even though the morning air temperature was already approaching 100 degrees. I spent the day conducting a more systematic investigation of the area, using metal detectors and ground-penetrating equipment to search for the missing thermometer. The instruments indicated metallic objects buried approximately 3 feet below the surface, directly beneath the cold circle. I excavated carefully with a small trenching shovel, digging down through the hardpan and mineral deposits. At exactly 3 feet depth, I found all 3 thermometers, buried in perfectly undisturbed earth, with no sign of any excavation or disturbance. The soil layers above the thermometers showed no evidence of recent digging, no loose earth, no changes in compaction, no tool marks or displacement that would indicate someone had buried the instruments. The ground surface looked exactly as it had the previous day, completely undisturbed hardpan with the characteristic salt crystallization patterns. But the thermometers were definitely buried 3 feet down, as if they had somehow sunk through solid earth without leaving any trace of their passage. I returned to the park headquarters and reported the missing equipment recovery to Jennifer. She listened to my description of the burial discovery with considerable skepticism. "Ryan, someone must have buried those thermometers as a prank," she said after I explained how I'd found them. "Maybe other park employees or visitors who wanted to see how you'd react." But I knew that wasn't possible. The monitoring site was 15 miles from the nearest road, accessible only by hiking across trackless desert terrain. No casual visitors reached that area, and no park employees had been assigned to work in that sector. More importantly, the earth above the thermometers showed no sign of excavation. Burying objects 3 feet deep requires significant digging, and hard-pan soil retains evidence of disturbance for weeks or months in Death Valley's arid conditions. Jennifer agreed to visit the site with me the following week. We'd conduct a more thorough investigation using professional equipment and document whatever was causing the temperature anomaly. When we reached the cold spot 7 days later, Jennifer confirmed my temperature measurements with her own instruments. The circular area maintained exactly 32 degrees surface temperature, despite ambient air temperatures of 118 degrees. "This is definitely impossible," she admitted after spending an hour documenting the thermal boundaries. "There's no natural process that could account for this kind of localized cooling in Death Valley." We left 4 thermometers at the site overnight, each one marked with fluorescent tape and GPS coordinates to prevent loss or confusion. The next morning, all 4 thermometers were buried 3 feet underground in perfectly undisturbed earth. Jennifer excavated them herself, documenting the burial conditions with photographs and soil analysis. The hardpan above the instruments showed no evidence of recent disturbance, no changes in compaction or crystallization patterns that would indicate excavation and refilling. "Something is pulling these instruments underground," she said, as we packed up the equipment. "But I have no idea what natural process could account for that kind of subsurface movement." We spent the next month conducting additional tests, leaving different types of monitoring equipment at the cold spot and documenting their disappearance and burial. Metal thermometers, plastic sensors, electronic data loggers, everything ended up 3 feet underground by morning, buried in earth that showed no sign of disturbance. The official environmental monitoring report classified the site as an unexplained thermal anomaly requiring further investigation. The equipment disappearances were noted but not explained, and the area was marked for long-term observation. But I've been back to the cold spot 6 times since then, always on my own time. The temperature remains constant at 32 degrees, and every instrument I leave there overnight disappears 3 feet underground through perfectly undisturbed earth. I've tried anchoring thermometers to the surface with metal stakes, burying them partially to prevent movement, even chaining them to heavy rocks. Nothing makes any difference. By morning, the instruments are always 3 feet down, and the surface shows no trace of excavation. The thing that disturbs me most isn't the impossible temperature differential, although that violates every principle of desert thermodynamics I understand. It's the precision of the burial depth, always exactly 3 feet, always in perfectly undisturbed earth, always with no evidence of the process that moved solid objects through solid ground. Something beneath that circular area of Death Valley is drawing metal and plastic objects downward through hard-pan soil that should be impermeable to vertical movement. The cold spot acts like a thermal sink, maintaining freezing temperatures in one of the hottest environments on Earth. I don't know what natural process could create such localized cooling effects or move solid objects through solid earth without leaving traces. But somewhere in Death Valley, there's a 10-foot circle where the normal rules of heat transfer and soil mechanics stop working, where instruments disappear into ground that refuses to show evidence of their passage. And I have the terrible feeling that the cold spot is just the surface manifestation of something much deeper. A zone where the normal laws of physics break down and objects can move through solid matter according to rules we're not supposed to understand. My name is Susan Martinez, and I've been an acoustic geologist with the University of Utah for 19 years. Most of that time has been spent studying how sound travels through different rock formations, measuring echo patterns in canyons and caves, and documenting the acoustic properties of geological structures throughout the Colorado Plateau. I know how sound behaves in confined spaces, how echoes reflect off canyon walls, and how to calculate the relationship between distance and acoustic delay. I thought I understood the physics of sound propagation, how acoustic waves travel at predictable speeds through air and rock, how echoes return according to measurable principles of reflection and distance. I was wrong about the relationship between sound and time in certain geological spaces. In October of 2023, I was conducting acoustic research in the remote canyon country of southeastern Utah, documenting sound propagation patterns in narrow slot canyons for a study on geological acoustics. The project involved measuring echo delays in various canyon configurations, creating acoustic maps that could help other researchers understand how sound behaves in different types of rock formations. The research site was in a particularly isolated section of canyon country, accessible only by a challenging 4-wheel drive route followed by several miles of hiking through trackless desert terrain. The canyon system I was studying consisted of narrow sandstone passages carved by water over millions of years, creating perfect acoustic chambers with smooth walls and complex geometric configurations. I'd been working in canyon acoustics for over a decade, and I was familiar with the typical sound patterns found in Utah's slot canyons. Most produce echoes with delays of 2 to 8 seconds, depending on the width and depth of the passages. The sound quality is usually excellent, clear reflections off smooth sandstone walls that preserve the original acoustic characteristics with minimal distortion. On Tuesday afternoon, I was testing the acoustic properties of a particularly deep and narrow canyon passage using standard techniques for measuring echo delay and sound quality. The procedure involves calling out or clapping hands, then timing the delay before the echo returns from the canyon walls. I started with simple vocal tests, calling hello into the canyon and measuring the time delay before hearing the echo return. In most Utah slot canyons, this produces an echo within 3 to 5 seconds, depending on the distance to the reflecting surfaces. But in this canyon, nothing came back. I waited 10 seconds, then 20, then a full minute. No echo returned from my initial call. I assumed the canyon geometry was absorbing sound rather than reflecting it, which can happen in passages with irregular walls or acoustic dampening materials. I tried again, this time calling more loudly and listening carefully for any reflected sound. Still nothing. I waited 5 minutes, then 10, thinking that perhaps the acoustic delay was longer than usual due to complex internal geometry. After 15 minutes of silence, I moved deeper into the canyon and tried calling from a different location. The passage was narrow enough that I could touch both walls with outstretched arms, and the smooth sandstone surfaces should have produced excellent acoustic reflection. I called testing into the depths of the canyon and waited for the echo. 3 hours later, I heard it come back. Not 3 seconds, or even 30 seconds, 3 hours. I was preparing to hike back to my vehicle when I heard my own voice calling testing from deep within the canyon, returning with perfect acoustic clarity but impossibly delayed. Sound doesn't travel that slowly. Acoustic waves move at approximately 1,100 feet per second through air at sea level, and even accounting for complex reflections off multiple canyon walls, echo delays should be measured in seconds, not hours. I checked my watch and my field notes to confirm the timing. I'd called testing at 2:37 p.m., and the echo returned at 5:39 p.m. 3 hours and 2 minutes of acoustic delay in a canyon passage that was probably less than a quarter mile deep. I spent the rest of the afternoon conducting additional acoustic tests, calling different words and phrases into the canyon, while carefully recording the times. Each test produced the same impossible result, echoes returning approximately 3 hours after the original sound, as if the acoustic waves were traveling through some medium much denser than air. That evening at my camp, I reviewed the acoustic principles that govern sound propagation and echo formation. There was no known physical process that could account for 3-hour acoustic delays in normal atmospheric conditions. Sound waves don't slow down and speed up. According to unknown variables, they travel at predictable speeds, determined by air temperature, humidity, and pressure. The next morning, I returned to the canyon with professional recording equipment, planning to document the impossible acoustic delays with precision instruments. I wanted to record both the original sounds and the delayed echoes, creating a complete acoustic record of whatever was happening in the canyon. But when I reached the test site, I discovered something more disturbing than the delayed echoes. The canyon was filled with sound. My voice from the previous day was still echoing through the rock passages, not just the testing call I'd heard return after 3 hours, but all the acoustic tests I'd conducted during the afternoon. Every word, every phrase, every sound was bouncing back and forth between the canyon walls in an endless loop. I could hear hello returning every few minutes, followed by testing, then other words and phrases I'd called out during Tuesday's research. The sounds were slightly distorted by repeated reflections, but still clearly recognizable as my own voice from the previous day. According to acoustic physics, echoes should fade away after a few reflections due to energy loss and acoustic dampening. Sound waves lose intensity each time they bounce off surfaces, and even the most reflective materials absorb some acoustic energy. Echoes don't continue indefinitely. They decay and disappear within seconds or minutes. But my voice from Tuesday afternoon was still bouncing through the canyon on Wednesday morning, creating a continuous acoustic loop that violated every principle of sound propagation I understood. I set up my recording equipment and documented the ongoing echo patterns, capturing audio samples of my own voice, returning from the canyon depths in an endless cycle. The recordings clearly showed the same words and phrases I'd called out the previous day, cycling through the canyon system with intervals of several minutes between repetitions. As I listened to the continuing echoes, I noticed something that disturbed me more than the impossible acoustic delays. The repeated reflections were slowly changing the content of my voice. Not just distortion from multiple bounces off rock walls, actual changes in the words themselves. Hello was becoming help, and testing was starting to sound like trapped. The acoustic modifications were subtle but consistent, as if the canyon walls were gradually transforming my research calls into something that sounded like distress signals. The phonetic changes followed patterns that seemed almost intentional, converting neutral scientific vocabulary into words that suggested urgency or danger. I called Dr. Robert Chen at the University of Utah to report the impossible acoustic conditions I was documenting. "Susan, that's not possible," he said when I described the 3-hour echo delays and continuing sound loops. "Acoustic waves don't behave that way in normal atmospheric conditions. You might be dealing with some kind of unusual atmospheric phenomenon, but sound doesn't slow down and loop indefinitely." I sent him digital audio files of the recorded echoes, including time-stamped recordings that clearly showed my voice returning hours after the original calls. He called me back that evening, sounding puzzled and concerned. "I've analyzed your recordings, and I can't explain what you're documenting," he admitted. "The acoustic delays are definitely real, but there's no known physical process that could account for them." He suggested that I might have discovered some kind of previously unknown acoustic phenomenon related to the specific geometry and mineral composition of the canyon walls. But even he seemed skeptical that natural processes could account for such extreme deviations from normal sound propagation patterns. I spent 2 more days at the research site, documenting the continuing echo loops and measuring the acoustic properties of the canyon with precision instruments. The sound patterns remained consistent, my voice from Tuesday continuing to bounce through the rock passages, gradually becoming more distorted and phonetically modified with each repetition. By Friday morning, the echoing words had changed significantly. Hello had become help me, testing had become trapped here, and other research vocabulary had transformed into what sounded like increasingly desperate calls for assistance. The acoustic modifications were creating the impression that someone was calling for help from deep within the canyon system, using my own voice, but with message content that I'd never actually spoken. I packed up my equipment and hiked out on Friday afternoon, disturbed by the implications of what I'd documented. My research calls were still echoing through the canyon when I left, continuing their endless acoustic loop with content that no longer resembled the original scientific vocabulary. The official research report documented the unusual acoustic properties of the canyon, but avoided speculation about the physical processes involved. The audio recordings were archived in our university database as examples of unexplained acoustic phenomena requiring further investigation. But I've been back to that canyon twice since then, always on my own time. The acoustic loops are still active, not just my voice from October 2023. But apparently the voices of everyone who has ever called into those rock passages, layered into a continuous soundtrack of echoing human speech. The thing that haunts me most isn't the impossible acoustic delays, although those violate every principle of sound physics I understand. It's the way the canyon walls gradually modify speech content, transforming innocent research calls into apparent distress signals that echo endlessly through the rock formations. I don't know what acoustic properties allow sound waves to travel for hours before reflecting, or how repeated echoes can change the phonetic content of human speech. But somewhere in Utah's canyon country, there's a slot canyon where sound behaves according to rules that operate outside our understanding of acoustic physics. And I have the terrible feeling that everyone who calls into those rock passages eventually hears their own voice calling back for help, trapped in an endless acoustic loop where speech gradually transforms into pleas for rescue that will echo through the stone forever.